There is a moment just before full wakefulness when the world feels perfectly complete. You are lying still, and the ceiling above you is solid. The mattress beneath you is real. The air moving through your lungs carries weight and temperature and the faint smell of morning. Everything is present. Everything is accounted for. The walls hold their positions. The floor does not waver. The objects around you, a lamp, a glass of water, a folded piece of clothing draped over a chair, occupy their places with a kind of quiet authority, as if they have always been there and always will be. In that half-conscious moment, the universe feels full. It feels dense with presence, layered with texture, humming with the low, reliable frequency of things that exist. This feeling is not a mistake exactly. It is a report from your senses, and your senses are doing precisely what they were shaped to do across hundreds of millions of years of biological refinement. They are filtering, they are selecting, they are presenting you with a version of reality that is useful, navigable and survivable. The warmth of the glass in your hand, the resistance of the floor beneath your feet, the solidity of the wall when you press your palm against it. These are real experiences. They are not hallucinations. But they are also not the full picture. They are, in a very precise and unsettling sense, a curated performance, a translation. And like all translations, something essential has been left out. What has been left out is almost everything. And that is not a poetic exaggeration. It is, as closely as science can currently measure, a literal description of the universe we inhabit. The world that feels so full, so dense, so reliably present, that world is, at nearly every scale we can examine, composed primarily of absence. The matter you can see, touch, and stand on represents a vanishingly thin layer of structure floating inside an ocean of nothing. The solidity you feel is not the universe's natural condition. It is the exception. It is the anomaly. And once you begin to understand the true proportions, the feeling of fullness never quite returns in the same way. Stay with this, because what follows is not a simple lesson about scale. It is something stranger and more disorienting than that. It is an invitation to look at the universe as it actually is, rather than as your nervous system has been trained to present it. This is what Beyond the Universe is here for, to move past the comfortable boundary of ordinary perception and into the territory where the real nature of things begins to reveal itself, not with comfort, not with easy resolution, but with the slow, patient honesty that the cosmos deserves. Begin with the room again. Begin with the wall. You can press your hand against it and feel resistance, and that resistance is genuine. The wall does not yield. The wall does not pass through you. The wall behaves exactly as a solid object should. But now consider what that wall is actually made of. Follow the material downward through its layers, past the paint, past the plaster, past the structural material beneath. Follow it into the molecular level, where the compounds that make up the wall are arranged in patterns, bonded together by electromagnetic forces, forming the lattice of matter that gives the wall its apparent solidity. And then go deeper still. Go past the molecules into the atoms themselves. An atom is not what most people picture when they hear the word. The common image, a small dense ball with other small balls orbiting around it like a miniature solar system, is a useful approximation, but it is also profoundly misleading in one critical respect. It suggests that an atom is a compact, filled object. It suggests that the components of an atom are close together, that the space inside an atom is occupied, that matter at its most fundamental level is in fact matter. But this is not what an atom looks like when you examine the proportions honestly. You've looked into the void. You didn't look away. If that means something to you, subscribe to Beyond the Universe. More descents are coming. Each one goes further than the last. The darkness has no end. Neither do we. The nucleus of an atom, the dense central region containing protons and neutrons, is extraordinarily small relative to the total volume of the atom. If you were to take a single hydrogen atom and expand it to the size of a large cathedral, the nucleus at its center would be roughly the size of a grain of sand. A single grain of sand, sitting on the floor of a vast stone building, surrounded by nothing but empty space all the way to the walls, the ceiling, the farthest corners. The electron, that single electron orbiting the hydrogen nucleus, would be somewhere out near those walls. A point so small it barely registers as a physical object at all, tracing its probabilistic path through a volume that is, by any honest measurement, almost entirely empty. This is not a metaphor constructed for dramatic effect. This is the actual geometry of matter. The atom, which is the fundamental unit of everything you have ever touched, everything you have ever seen, everything you have ever been, is overwhelmingly composed of void. The nucleus occupies roughly 1/100,000th of the atom's diameter. In terms of volume, the nucleus takes up approximately 1/10 trillionth of the total space the atom occupies. The rest is nothing, not thin air, not a diffuse medium, not some subtle substance we haven't named yet. Nothing. Empty space, crossed only by the invisible fields of force that hold the structure together. And this is where the first real vertigo begins. Because if the atom is mostly empty, and if everything you can see and touch is made of atoms, then everything you can see and touch is also mostly empty. The wall is mostly empty. The floor is mostly empty. Your hand, pressed against the wall, is mostly empty. Two vast collections of almost nothing, pressing against each other, held apart not by the collision of solid surfaces, but by the electromagnetic repulsion between electron clouds. A force, not a substance. The sensation of solidity is real, but what produces it is not the presence of matter. It is the behavior of fields. It is the interaction of forces operating across distances that, at the atomic scale, are almost incomprehensibly large relative to the particles involved. Let that settle for a moment. The hardest, densest, most unyielding object you have ever encountered, a granite countertop, a steel beam, a diamond, is, in terms of the actual ratio of matter to space within it, almost indistinguishable from a vacuum. If you could somehow remove all the empty space from every atom in the human body, compressing only the actual nuclear and subatomic material together, the entire human body would shrink to a size invisible to the naked eye. All of humanity, every person who has ever lived, every body that has ever walked this planet, compressed to its actual material content, would fit within a volume smaller than a sugar cube. The rest of what we are, the rest of what we feel ourselves to be, is the architecture of forces operating across emptiness. This is the first layer of the revelation, and it is already deeply strange, but it is also, in a way, still intimate, still local, still contained within the scale of things we can at least conceptually approach: atoms, molecules, the microscopic world. The strangeness here is philosophical more than spatial. It challenges our intuition about solidity, about presence, about what it means for something to exist, but it does not yet challenge our sense of place. We are still in this first layer of understanding, standing in a room on a planet inside a solar system within a galaxy, surrounded by what feels like a universe full of stars and light and matter. But it gets worse, because the emptiness inside matter is only the beginning. It is the smallest and most intimate version of a pattern that repeats itself at every scale the universe contains, growing larger and more absolute with each step outward. The void inside the atom is a preview, a whisper of what is coming, and what is coming is not smaller or more manageable. It is larger, colder, and far more complete. Step outside the atom, step outside the molecule, the cell, the body, the building, the city. Rise above the surface of the Earth and look down at the planet from a distance. From low orbit, the Earth still looks full. It looks dense with geography, continents and oceans, mountain ranges and river deltas, the thin, luminous skin of the atmosphere catching sunlight at the edges. It looks like a place. It looks like the kind of object that belongs in a universe full of similar objects. A universe where matter is the norm and space is merely the background against which matter arranges itself. But now pull back further. Pull back until the Earth is a small blue point, and the Moon is a smaller gray point beside it, and the distance between them becomes visible. That distance is roughly 384,000 kilometers. In human terms, this is an enormous number. It is the kind of number that resists intuition. If you drove a car at highway speed without stopping, it would take you more than 5 months to cover that distance. If you walked, it would take years. And yet, in the context of the solar system, the distance between the Earth and the Moon is almost negligible. It is a short step, a local relationship, two objects that are, by cosmic standards, practically touching. Now pull back further still. Pull back until the sun becomes visible, a bright point at the center of the system, and the Earth a tiny speck orbiting it at a distance of approximately 150 million kilometers. This distance is so large that light traveling at 300,000 kilometers per second takes about 8 minutes to cross it. 8 minutes for the fastest thing in the universe to travel from the sun to the Earth. And yet this too is still a local relationship. The sun and the Earth are neighbors. They are bound together by gravity, locked in an intimate gravitational embrace that has persisted for 4.5 billion years. But now consider the full extent of the solar system. Consider the outer planets, Jupiter, Saturn, Uranus, Neptune, orbiting at distances that dwarf the Earth-Sun gap. Neptune, the outermost of the major planets, orbits the Sun at a distance of roughly 4.5 billion kilometers. Light takes more than 4 hours to make that journey. And beyond Neptune, The solar system continues, the Kuiper belt, the scattered disk, the distant reaches of the Oort cloud, a vast spherical shell of icy bodies extending perhaps a quarter of the way to the nearest star. The full gravitational domain of the Sun stretches across a volume of space so large that it takes light years to cross it. And within all of that volume, within the entire gravitational territory of our star, encompassing billions of kilometers in every direction, the actual matter is almost nothing. The planets, the moons, the asteroids, the comets, the dust, all of it, gathered together, would represent a tiny fraction of the total volume of the solar system. If you were to shrink the solar system to the size of a football field, the Sun would be a small marble near one end, and the planets would be specks of dust scattered across the grass, separated by distances that would make them nearly impossible to find. The space between them would be the dominant feature, not the objects, the space. This is the second layer, and it is already beginning to feel different from the first. The emptiness inside the atom was strange and philosophical. It challenged our sense of what matter is. But the emptiness of the solar system is spatial and visceral. It is the kind of emptiness you could, in principle, travel through. It is the kind of emptiness that has a direction, a temperature, a quality. It is cold. It is dark. It is silent in a way that no place on Earth can replicate, because on Earth there is always something: air, vibration, the faint electromagnetic noise of a living planet. But in the space between planets, there is almost nothing to carry any signal at all. The silence is not the absence of sound, it is the absence of the medium through which sound could exist. And this leads to something more disturbing, because the solar system, for all its emptiness, is still a structured place. It has a center, it has orbits, it has the organizing influence of the Sun's gravity, which holds everything in its domain in a kind of loose but persistent relationship. The planets are isolated, yes, but they are not random, they are arranged. They are connected, however tenuously, by the invisible threads of gravitational force. The solar system, despite its vast internal emptiness, is still a system. It still has the quality of belonging, of objects that are, in some meaningful sense, together. But now step outside the solar system entirely. Step out into the space between stars. And here, the nature of emptiness changes again. Here, it becomes something that the word empty almost fails to describe adequately. Because the word empty still implies a container, a space that could, in principle, be filled. What lies between the stars is not merely unfilled space. It is space on a scale so vast that the very concept of filling it becomes meaningless. The nearest star to our Sun is Proxima Centauri, a small red dwarf located approximately 424 light-years away. A light-year is the distance light travels in 1 year, roughly 946 trillion kilometers. So Proxima Centauri is approximately 40 trillion kilometers from the Sun. If the solar system were the size of a coin, a small ordinary coin you might hold between your fingers, then Proxima Centauri would be located roughly 1.3 kilometers away from that coin, not across the room, not across the building, more than a kilometer away in open space with nothing between them but void. And Proxima Centauri is our nearest neighbor. It is the closest other star in the entire galaxy. Every other star is farther. Most stars in the Milky Way are separated from their neighbors by distances measured in light years. Distances so large that even the fastest spacecraft humanity has ever built would take tens of thousands of years to cross them. The Voyager 1 probe, launched in 1977 and now the most distant human-made object ever sent into space, is traveling at roughly 17 kilometers per second. At that speed, it would take approximately 75,000 years to reach Proxima Centauri, if it were headed in that direction. Which it is not. The stars, in other words, are not close. They are not scattered thickly through space like lights on a ceiling. They are isolated points, separated by distances that make the emptiness of the solar system look intimate by comparison. The night sky, which appears to the naked eye as a dense field of light, is in reality a projection, a two-dimensional illusion created by the fact that our eyes cannot perceive depth at cosmic distances. What looks like a crowded field of stars is actually a collection of objects separated by years of travel at the speed of light, each one alone in its own vast territory of darkness. But it goes deeper, because even the description of stars as isolated points separated by light years does not fully capture the quality of the emptiness between them. The interstellar medium, the material that fills the space between stars, is not a true vacuum. It contains gas and dust, magnetic fields and cosmic rays, the occasional molecule drifting through the dark, but the density of this material is almost incomprehensibly low. In the densest regions of interstellar space, there are perhaps a few hundred atoms per cubic centimeter. In the more typical regions, there are fewer than 1 atom per cubic centimeter. For comparison, the air you are breathing right now contains approximately 27 billion atoms per cubic centimeter. The interstellar medium is not thin air. It is not even a laboratory vacuum. It is a near-perfect emptiness that makes the best vacuum humans have ever created in a laboratory look dense by comparison. And yet even this, even the vast, cold, almost perfect emptiness between the stars, is not the deepest layer. It is not the most extreme version of cosmic absence. It is, in fact, still a relatively populated region of the universe because it exists within a galaxy. It exists within the Milky Way, a structure containing somewhere between 100 billion and 400 billion stars, all bound together by gravity into a rotating disk roughly 100,000 light-years across. Within the galaxy, stars are separated by light-years. But the galaxy itself is a structure. It has density. It has organization. It has the quality of being a place where things are, even if those things are separated by enormous distances. The real emptiness, the emptiness that begins to feel less like a physical property and more like a fundamental condition of the universe, lies between the galaxies. And that is where this descent is heading. But before we arrive there, it is worth pausing to consider what has already been established, because the implications are already significant enough to be unsettling. You began this journey in a room. You felt the floor beneath you, the air around you, the solid, reliable presence of the physical world. And now, having descended only 2 layers into the structure of that world, into the atom and into the solar system, you have already discovered that the reality you inhabit is composed, at both its smallest and its largest accessible scales, primarily of nothing. The solidity of the floor is a force, not a substance. The fullness of the solar system is an illusion created by the fact that you cannot see the distances between the objects within it. The matter you stand on, the matter you are made of, the matter that constitutes everything you have ever known, is a thin, improbable film of structure stretched across an ocean of void. And the ocean is deeper than you have yet been shown, far deeper. The layers that remain, the interstellar distances, the intergalactic abysses, the cosmic voids, the invisible architecture of dark matter, the accelerating expansion of space itself, the long, cold future of a universe trending toward maximum emptiness. These are not variations on the theme already established. They are escalations of it. Each one reveals a universe that is not merely larger than we imagined, but emptier than we imagined, and emptier in ways that carry consequences for everything we think we understand about existence, about structure, about the possibility of connection across cosmic distances. But for now, stay here. Stay in this first layer of understanding. Let the atom settle into its true proportions, that vast cathedral of empty space with its grain of sand nucleus. Let the solar system settle into its true proportions, that football field of void with its marble sun and its dust-speck planets. Let the interstellar distances settle, those 40 trillion kilometers of cold silence between our star and its nearest neighbor. Let these numbers sit in your mind not as abstract quantities but as physical realities, as descriptions of the actual space you inhabit, the actual universe in which your planet orbits, the actual context in which every human life has ever been lived. Because the context matters. The context is not background. The context is the dominant feature. The emptiness is not the space between the interesting things. The emptiness is the thing. The matter, the stars, the planets, the atoms, the bodies, the rooms, the walls, the floors, all of it is the exception. All of it is the rare, improbable, temporary deviation from the universe's overwhelming preference for nothing. There is a quality to this realization that is difficult to name precisely. It is not quite fear, though it has fear's texture. It is not quite awe, though it has awe's scale. It is something closer to the feeling of standing at the edge of a very high place and looking down. Not the fear of falling, but the sudden, visceral awareness of the distance between where you are and where the ground is. The awareness that the space between you and the bottom is real, and large and indifferent to your presence. That is the feeling that the true scale of cosmic emptiness produces, once it begins to be genuinely understood, rather than merely acknowledged. And the understanding is only beginning. The atom and the solar system are the first 2 steps of a descent that goes much, much further. The distances that remain to be crossed, in imagination, in comprehension, in the slow work of genuinely grasping what the universe actually is, are not larger versions of what has already been described. They are different in kind. They are emptiness operating at scales where the very concepts of distance and isolation begin to lose their ordinary meanings and acquire new ones. stranger, and more final. Consider again the wall of your room. Consider the paint on that wall and the molecules of pigment suspended in it, and the atoms that compose those molecules, and the vast empty spaces inside those atoms. Consider that every atom in that wall is separated from every other atom by distances that, relative to the size of the atoms themselves, are enormous. Consider that the wall, which appears to your eyes as a continuous, unbroken surface, is in reality a collection of discrete particles separated by void, held in their arrangement not by contact but by force. The wall is not touching itself. Its components are hovering near each other, held in place by electromagnetic interactions, maintaining the appearance of solidity through the constant, invisible work of physics. Now consider that this same principle, the principle of apparent fullness concealing actual emptiness, operates at every scale above the atomic. The solar system appears full because we cannot see the distances between its components. The galaxy appears dense because we cannot perceive the light years between its stars. The universe appears populated because the night sky compresses three-dimensional depth into a two-dimensional field of light. At every scale, the appearance of fullness is a perceptual artifact. It is what emptiness looks like when you are too small, too local, and too embedded within it to see it clearly. This is the central deception that the universe perpetrates on every conscious observer embedded within it. Not through malice, the universe has no intentions, but through the simple geometry of scale. When you are small enough and local enough, and surrounded by enough structure on your own level, the emptiness above and below and between that structure becomes invisible. You see the matter, you do not see the void. You feel the floor, you do not feel the 99% of the atom that is not there. You look at the night sky and see stars. You do not see the years of empty space between them. But the void is there. It has always been there. It is, in the most literal sense, the dominant feature of the universe. And as the scale of observation increases, as we move from the atom to the solar system to the galaxy, to the cosmic web, to the observable universe itself, the void does not diminish. It grows. It deepens. It becomes more absolute, more pervasive, more clearly the fundamental condition of everything that exists. The matter, all of it, every atom of every star of every galaxy in the observable universe, represents approximately 5% of the total energy content of the cosmos. 5%. The rest is something else entirely, something that does not emit light, does not reflect light, does not interact with ordinary matter in any way that our instruments can directly detect. Something that is, in the most profound sense, invisible. And that invisible something is not empty space. It is a presence, a structure, a shaping force that has been operating since the earliest moments of the universe's existence, guiding the formation of everything we can see, holding the architecture of the cosmos together from the inside of a darkness we cannot penetrate. But that revelation belongs to a later layer of this descent. For now, the 5% is enough to sit with. 5%. Everything you have ever seen, touched, measured, or imagined. Every planet, every star, every galaxy, every atom of every living thing that has ever existed anywhere in the universe, all of it together, constitutes 5% of what the universe contains. The other 95% is something we can barely describe, let alone understand. And even within that 5%, as we have already seen, the actual matter is separated by distances so vast that the matter itself is almost irrelevant to the total volume it occupies. The universe is not full. It never was. The feeling of fullness, that warm, reliable morning light sensation of a world dense with presence, is a gift from your nervous system, a carefully constructed interface between your consciousness and a reality that your consciousness was never designed to perceive directly. It is a useful gift. It is a necessary gift. Without it, the cognitive weight of the actual universe would be paralyzing. But it is not the truth, and the truth, once glimpsed, does not go away. There is something almost tender about the way the human mind protects itself from this knowledge. The brain is extraordinarily good at operating at the scale of human life, at the scale of rooms and bodies and faces and distances measured in meters and kilometers. It is good at this because this is the scale at which survival happens, at which relationships form, at which meaning is constructed and maintained. The cosmic scale is not useful for survival. The emptiness of the atom does not help you find food or shelter or connection. The distance to the nearest star does not inform any decision you will ever need to make, so the brain filters it out. It presents you with the version of reality that matters for the life you are actually living. But there is a cost to this filtering. The cost is a persistent, low-level misunderstanding of what the universe actually is, a misunderstanding that shapes in subtle ways how we think about existence, about permanence, about the significance of structure and matter in life. We live as if matter is the norm and emptiness is the exception. We live as if the universe is fundamentally full, and the spaces between things are merely the gaps between the important parts. We live as if the cosmos is, at its heart, a place of presence rather than absence. And the universe, if it could be said to have a perspective on this, would disagree, quietly, without drama, with the patient, absolute indifference of something that has been mostly empty for 13.8 billion years and intends to remain so, in increasingly complete ways for a duration that makes 13.8 billion years look like a brief, bright morning. The descent continues, the layers deepen, and each layer as it opens reveals not a universe that is merely larger than the one before, but one that is emptier, colder, more indifferent, and more final. The atom was the first step, the solar system was the second. What lies beyond? The interstellar distances, the galactic scales, the cosmic voids, the invisible architecture of dark matter, the accelerating expansion driven by dark energy, the long thermodynamic future of a universe cooling toward absolute stillness. These are not simply bigger versions of what has already been described. They are something else. They are the universe showing its true face. And the face is not hostile. It is not cruel. It is simply vast and dark and almost entirely empty. And it has been this way since long before the first star ignited, and it will be this way long after the last one fades. The matter, the 5%, the thin, improbable film of structure, is a temporary condition, a brief disturbance in the dark, and the dark is patient. For now, though, you are still in the room. The floor is still beneath you. The wall is still solid to the touch. The morning light is still coming through the window, and the world still feels full and present and real. Hold on to that feeling for a moment longer, not because it is true, but because it is yours, because it is the feeling of being alive inside a universe that is almost entirely empty, and somehow, against all probability, finding yourself in one of the rare places where matter has gathered and organized and persisted long enough to become aware of itself. That awareness is extraordinary. It is also, in the context of the universe's true proportions, almost impossibly fragile. A thin layer of organized complexity clinging to the surface of a small rocky planet, orbiting an ordinary star in the outer regions of a spiral galaxy, in a universe that is 99.99999% void and trending toward more. The awareness is real, the fragility is real, and the emptiness surrounding it, above it, below it, inside it, between every atom of every cell of every body that has ever been conscious, is real too. Step outside, not metaphorically, actually step outside in your mind, and stand under an open sky. It does not matter whether it is day or night. What matters is the direction you are facing when you look up. You are looking outward. You are looking away from the planet, away from the surface, away from the thin biological film that coats this rock and calls itself the world. You are looking into the solar system, and beyond it, and the first thing to understand about that direction is that it is mostly nothing. Not mostly nothing in the way a clear sky is mostly nothing. A clear sky is full of air, full of molecules, full of the invisible medium that carries sound and weather and the chemistry of life. The direction above the atmosphere is a different kind of mostly nothing. It is the kind that does not end. The atmosphere itself, that thin, precious shell of gas that makes all biological life on this planet possible, extends to roughly 100 kilometers above the surface before it fades into the near vacuum of space. 100 kilometers. If the Earth were the size of a standard classroom globe, the atmosphere would be thinner than a coat of paint on its surface. Everything that has ever breathed, everything that has ever flown, every cloud that has ever formed, every storm that has ever turned, all of it happens within that coat of paint. Below it is rock and water, and the slow churning of a living planet. Above it is the solar system, and the solar system is almost entirely empty. The moon is the first object you encounter as you move outward from Earth, and the moon is already far enough away that the distance begins to strain ordinary intuition. 384,000 kilometers. But the moon is also, in the context of the solar system, essentially adjacent to the Earth. They are a pair. They move together through space, locked in a gravitational relationship that has shaped the tides, stabilized the Earth's axial tilt, and influenced the conditions under which life developed on this planet. The moon is close enough that humans have traveled to it. It took 3 days. 3 days of travel through a vacuum so complete that a single breach in the spacecraft's hull would have been immediately fatal. 3 days through a silence so absolute that no sound could exist within it, and the moon is the nearest thing. Beyond the moon, the distances grow quickly. Mars, at its closest approach to Earth, is roughly 54 million kilometers away. At its farthest, it is more than 400 million kilometers distant. The journey to Mars, with current propulsion technology, takes between 6 and 9 months. 6 to 9 months of travel through interplanetary space, through a void that contains on average a few atoms per cubic centimeter, threaded with solar wind and radiation, crossed by the occasional dust particle or small rock, but otherwise empty in a way that makes the word empty feel inadequate. 6 to 9 months, and you arrive at a planet that is, by solar system standards, a neighbor. Jupiter is 5 times farther from the Sun than the Earth. Saturn is nearly 10 times farther. Uranus is 19 times farther. Neptune is 30 times farther. These are not simply larger versions of the Earth-Moon distance. They are distances of a qualitatively different character. The Voyager 2 spacecraft, launched in 1977, reached Neptune in 1989. 12 years of continuous travel at speeds that would cross a continent in minutes. 12 years to reach the 8th planet of our own solar system. And Neptune is still, by any cosmic measure, practically in our backyard. But it gets worse, because the planets are not the edge of the solar system. They are not even close to the edge. Beyond Neptune lies the Kuiper Belt, a region of icy bodies and dwarf planets extending from roughly 30 to 50 astronomical units from the Sun. Beyond that lies the scattered disk, a more diffuse region of objects with highly elliptical orbits that can carry them hundreds of astronomical units from the Sun. And beyond that, far beyond, at distances between 2,000 and perhaps 100,000 astronomical units, lies the Oort cloud, a vast spherical shell of icy bodies that represents the outermost gravitational territory of the Sun. The Oort cloud has never been directly observed. It is inferred from the behavior of long-period comets that occasionally fall inward toward the Sun after being disturbed from their distant orbits. But if it exists as theorized, it extends roughly a quarter of the way to the nearest star. A quarter of the way to the nearest star. Think about what that means. The Sun's gravitational influence, the outermost boundary of what can reasonably be called the solar system, reaches approximately 1/4 of the distance to Proxima Centauri. And Proxima Centauri is 4.24 light-years away. So the solar system, at its most generous definition, extends roughly 1 light-year from the Sun in every direction. 1 light-year of gravitational territory, containing the Sun, 8 planets, dozens of moons, millions of asteroids, billions of comets, and the diffuse haze of the Oort cloud. And within all of that volume, within a sphere 1 light-year in radius, the actual matter is so sparse, so thinly distributed, that the solar system is, by volume, almost entirely empty space. Now, step outside the solar system. Step into the interstellar medium, the space between the stars. And here the character of emptiness changes in a way that is difficult to convey without sitting with it for a moment. Within the solar system, the emptiness is at least organized. It has a center. It has a structure. The Sun's gravity gives the void a shape, a direction, a sense of orientation. Even in the outer reaches of the Oort cloud, you are still, in some meaningful sense, somewhere. You are in the solar system. You belong to a system. In the interstellar medium, that sense of belonging disappears. Between the stars, there is no center. There is no organizing gravity pulling you toward anything in particular. There is no nearby source of light or heat. There is no reference point that would allow you to say, with confidence, that you are closer to one thing than another. There is only the void, the cold, dark, almost perfectly empty space between stellar systems, and the faint, ancient light of distant stars that tells you, if you can see it at all, that you are not at the absolute edge of everything, but that you are also not near anything. The density of the interstellar medium varies. In some regions, near star-forming nebulae, near the remnants of supernovae, the gas and dust can be relatively dense, at least by interstellar standards, but in the typical regions of the Milky Way's disk, the interstellar medium contains roughly 1 atom per cubic centimeter. 1 atom per cubic centimeter. The air in the room where you are sitting contains approximately 27 billion atoms per cubic centimeter. The interstellar medium is not thin, it is not dilute. It is, by any standard derived from human experience, essentially nothing. A near-perfect vacuum that extends for light-years in every direction, broken only by the occasional star, those rare, isolated furnaces of nuclear fire that represent the universe's most dramatic attempt to concentrate matter into something bright and warm and temporary. The stars themselves are worth considering in this context because the stars are often thought of as the universe's primary feature, the things that fill the night sky, the things that define the cosmos, the things that make the universe feel populated and alive. But the stars, for all their brilliance, are extraordinarily rare. In the Milky Way, there are somewhere between 100 billion and 400 billion stars. This sounds like an enormous number. It is an enormous number. But the Milky Way is also an enormous place. A disk roughly 100,000 light-years in diameter and several thousand light-years thick, with a total volume of approximately 8 trillion cubic light-years. Distribute 200 billion stars across 8 trillion cubic light-years, and the average distance between stars works out to roughly 4 to 5 light-years. Every star, on average, is alone in a sphere of empty space roughly 4 to 5 light-years in radius. This is the texture of the galaxy, not a dense field of stars, but a sparse scattering of isolated nuclear furnaces, each one separated from its neighbors by distances so vast that the light from one star, traveling at the maximum speed the universe permits, takes years to reach the next. The galaxy is not full. The galaxy is mostly empty, with stars scattered through it like rare, bright exceptions to the overwhelming rule of darkness. And this leads to something more disturbing, because even the galaxy, even the Milky Way with its hundreds of billions of stars and its complex structure of spiral arms and central bulge and dark matter halo, is not the largest unit of cosmic organization. It is not even close. The Milky Way is one galaxy among an estimated 2 trillion galaxies in the observable universe. 2 trillion. And those galaxies are not evenly distributed through space. They are clustered, grouped, arranged into structures of increasing scale. Galaxy groups, galaxy clusters, superclusters, all of it forming a vast three-dimensional web of matter that stretches across the observable universe. And between the strands of that web, between the filaments and sheets and nodes where galaxies cluster together, there are regions of space so empty that they make the interstellar medium look crowded. These regions are called cosmic voids, and they are the universe's most extreme expression of emptiness. A typical cosmic void is between 100 and 300 million light-years across. Some of the largest known voids are even larger. The Buddha's void, for example, is approximately 330 million light-years in diameter, a roughly spherical region of space that contains almost no galaxies at all. Not a few galaxies, not a sparse scattering of isolated stars, almost nothing. A sphere of space 330 million light-years across, and within it, the near total absence of matter. To appreciate what 330 million light-years means, consider that the entire Milky Way galaxy is 100,000 light-years across. The Buddha's void is 3,300 times wider than the Milky Way. If you place the Milky Way inside the Buddha's void, it would be like placing a single grain of sand inside a room the size of a city. The void would swallow it without noticing, and the Buddha's void is not unique. It is one of many such voids distributed throughout the observable universe, each one a vast, dark, almost structureless region where the cosmic web has left almost nothing behind. The cosmic web itself is one of the most remarkable structures in the universe, and also one of the most revealing. When astronomers map the distribution of galaxies across large scales, what they find is not a random scattering. They find a pattern, a network of filaments, long, thin strands of matter connecting galaxy clusters, surrounding vast empty voids. The filaments are where the galaxies are, the voids are where they are not, and the voids are far larger than the filaments. The voids dominate. The structure, the web, the filaments, the clusters, is the minority. The emptiness is the majority. The cosmic web is not a web of matter suspended in space. It is a web of emptiness, with thin threads of matter tracing its boundaries. This inversion is important. When we think of the cosmic web, we tend to focus on the web, on the filaments, the clusters, the nodes where galaxies gather in their millions. We focus on the structure because structure is what we can see, what we can map, what our instruments can detect. But the structure is the exception. The voids are the rule. If you were to place yourself at a random location in the observable universe, the probability that you would find yourself inside a galaxy, or even near one, is extraordinarily small. The most likely outcome is that you would find yourself in a void, in one of those vast, dark, almost featureless regions where the cosmic web has left almost nothing behind. And in a void, the experience of the universe would be profoundly different from anything we know on Earth. There would be no nearby stars, no nearby galaxies. The night sky, if you could call it that, would be almost completely dark. The faint smudges of distant galaxy clusters, visible only at the edges of the void, would be the only evidence that the universe contained anything at all. The darkness would not be the darkness of a moonless night on Earth, where the Milky Way still arches overhead and the stars still crowd the sky. It would be a darkness of a different order, a darkness in which the nearest galaxy might be tens of millions of light-years away, and the nearest star might be hundreds of millions of light-years distant, a darkness in which the universe's preference for emptiness would be not a background fact but an immediate, overwhelming, inescapable reality. But it goes deeper, because the cosmic voids are not simply empty regions between the matter. They are, in a sense, the universe's natural state, the condition toward which the cosmos has been moving since the earliest moments after the Big Bang. In the first fractions of a second after the universe began, matter was distributed almost uniformly throughout space. There were tiny fluctuations, quantum variations in density that were amplified by the rapid expansion of the early universe, but the overall distribution was remarkably smooth. Over time, gravity acted on these fluctuations. Regions that were slightly denser than average attracted more matter, growing denser still. Regions that were slightly less dense than average lost matter to their denser neighbors, growing emptier still. The cosmic web is the result of 13.8 billion years of this process, gravity pulling matter together into filaments and clusters, leaving behind the voids that now dominate the universe's large-scale structure. The voids, in other words, are not accidents. They are not gaps in the structure that happen to be left unfilled. They are the product of the same gravitational processes that built the filaments and clusters. They are the negative space of cosmic structure, the emptiness that was created by the same forces that created the matter's organization. The universe did not start full and become empty. It started nearly uniform and became structured, and the structure it built was mostly void, with thin threads of matter tracing the boundaries between the empty regions. This is a subtle but important shift in perspective. The emptiness of the universe is not a failure of matter to fill space. It is the result of matter's own gravitational dynamics, the inevitable consequence of the way gravity works over cosmic time. Matter gathers, and when matter gathers, it leaves behind the places it gathered from. The voids are the shadows of the filaments. The emptiness is the price of structure. Every galaxy cluster, every filament, every node in the cosmic web represents a region of space that was emptied to fill it. Now consider the distances between galaxies, not the distances within the cosmic web, not the distances between galaxies in the same cluster or the same filament, but the distances between the major structures themselves. The Milky Way is part of a small group of galaxies called the local group, which contains roughly 50 to 80 galaxies, most of them small dwarf galaxies orbiting the two dominant members, the Milky Way and the Andromeda galaxy. The local group occupies a region of space roughly 10 million light-years across. Beyond the local group, the nearest major galaxy cluster is the Virgo cluster, approximately 53 million light-years away. Beyond that, the Laniakea supercluster, the vast cosmic structure of which the local group is a tiny peripheral member, extends across roughly 520 million light-years. These numbers are large enough to be almost meaningless in ordinary terms, but try to hold them in mind as physical distances, as actual separations between actual objects in actual space. The Andromeda galaxy, our nearest large galactic neighbor, is approximately 2.5 million light-years away. Light leaving Andromeda right now will not reach the Milky Way for 2.5 million years. When that light left Andromeda, our ancestors were early hominids, walking the African savanna with no concept of galaxies, no concept of light-years, no concept of the universe beyond the sky above them. The light that is reaching us now from Andromeda left that galaxy before our species existed, and Andromeda is our nearest large neighbor. The Virgo cluster is 53 million light-years away. Light leaving the Virgo cluster now will not reach us for 53 million years. When that light left the Virgo cluster, the dinosaurs had been extinct for roughly 13 million years, and the ancestors of modern horses were small, multi-toed creatures the size of dogs. The universe we observe is not the universe as it is. It is the universe as it was, a vast, layered archive of ancient light, each photon carrying information about a moment that is already millions or billions of years in the past by the time it reaches our instruments. And this temporal depth of the observable universe adds another dimension to the emptiness. Not only is the universe spatially empty, not only are the galaxies separated by distances that light takes millions of years to cross, but the universe we observe is also temporally empty in a sense. The most distant objects we can see are not the universe as it exists now. They are the universe as it existed billions of years ago, when the light we are now receiving first began its journey. The universe we inhabit in the present moment is, in a very real sense, invisible to us. We can only see its past. The present universe, the universe as it actually is right now at this moment, is hidden behind the light travel time that separates us from everything beyond our immediate cosmic neighborhood. But it gets worse. Because the universe is not static, it is not a fixed arrangement of galaxies sitting at fixed distances from each other, waiting for light to cross the gaps between them. The universe is expanding. Space itself is growing. The distances between galaxies are increasing, not because the galaxies are moving through space away from each other, but because the space between them is stretching. Every moment, the fabric of the cosmos is becoming larger, and the galaxies embedded in it are being carried apart by that expansion, like raisins in a rising loaf of bread, not moving through the dough, but being carried apart as the dough itself expands. This expansion has a profound consequence for the observable universe. Because light travels at a finite speed, and because the universe is expanding, there is a limit to how far we can see. There is a boundary, called the cosmic horizon, or the particle horizon, beyond which the universe is, in principle, unobservable, not because there is nothing there, but because the light from those regions has not had time to reach us in the 13.8 billion years since the Big Bang. The observable universe, the sphere of space from which light has had time to reach us, has a radius of approximately 46 billion light-years. Beyond that boundary, the universe continues, possibly forever, but we cannot see it. We cannot receive any signal from it. It is, for all practical purposes, beyond our reach, and the expansion is not slowing down. This is the detail that transforms the picture from merely vast to genuinely unsettling. For most of the universe's history, it was assumed, reasonably based on the physics of gravity, that the expansion of the universe would be slowing down. Gravity pulls matter together. The mutual gravitational attraction of all the matter in the universe should, over time, act as a brake on the expansion, slowing it, and perhaps eventually reversing it. This was the expected story. It was a story with a certain dramatic logic, a universe that expands, slows, and perhaps collapses back on itself in a final, fiery contraction. But in 1998, two independent teams of astronomers, studying the brightness of distant supernovae, discovered something that contradicted this expectation entirely. The expansion of the universe is not slowing down, it is speeding up. The universe is not decelerating under the influence of gravity, it is accelerating. The galaxies are not merely moving apart, they are moving apart faster and faster, driven by something that acts in direct opposition to gravity, something that fills space uniformly and pushes outward with a pressure that increases as space expands. This something was given the name dark energy, and it represents approximately 68% of the total energy content of the universe. Dark energy is one of the most profound mysteries in all of science. It is not matter. It does not clump or cluster. It does not interact with light or with ordinary matter in any detectable way. It is simply a property of space itself, a kind of intrinsic energy that empty space possesses, that causes space to expand at an accelerating rate. The more space there is, the more dark energy there is, and the faster the expansion accelerates. It is a self-reinforcing process, and it has been operating for roughly the last 5 billion years, gradually overcoming the gravitational attraction of matter and driving the universe toward a future of increasing isolation and separation. The implications of accelerating expansion are staggering, because if the expansion continues to accelerate, and there is currently no physical mechanism that would cause it to stop, then the galaxies beyond our local group will eventually be receding from us faster than light can travel between us and them. Not because they are moving through space faster than light, that would violate the laws of physics, but because the space between us and them will be expanding so rapidly that the distance will be growing faster than light can cross it. When that happens, those galaxies will pass beyond our cosmic horizon. Their light will never reach us again. They will become, in the most absolute sense, unreachable. This is already happening. The most distant galaxies we can currently observe are already receding from us at speeds greater than the speed of light due to the expansion of space. We can still see them because the light they emitted in the past, when they were closer, is still reaching us. But the light they are emitting now will never reach us. The universe we can observe is already smaller than the universe that exists, and it is getting smaller all the time. Not because the universe is shrinking, but because the expansion is carrying more and more of it beyond the horizon of what we can ever see or reach. In the far future, In billions of years, if the current understanding of dark energy is correct, the local group will be the only structure visible in the night sky. All other galaxies, all other clusters, all other superclusters will have receded beyond the cosmic horizon, their light redshifted into invisibility, their existence undetectable by any instrument. The universe will not have changed in any dramatic way. It will simply have expanded to the point where the distances between structures are so vast that no signal can cross them. The cosmos will not have ended. It will have separated. Each gravitationally bound structure, each galaxy, each cluster, will be an island, isolated in a sea of expanding space, unable to communicate with or even observe any other island. This is the shape of cosmic isolation, not the isolation of a single planet in a solar system or a single star in a galaxy, but the isolation of entire galaxies in a universe that has expanded beyond the reach of connection. The loneliness of the cosmos is not a metaphor. It is a physical process driven by dark energy, operating on timescales of billions of years, and it is already underway. The universe is not merely empty, it is becoming more empty, in the most fundamental sense, not by losing matter, but by expanding the space between matter until the matter can no longer interact, communicate, or even observe itself across the growing void. And within this expanding, isolating universe, the matter that does exist, the 5%, the thin film of structure, is itself not permanent. The stars are burning. They are consuming their nuclear fuel at rates that vary enormously from star to star, but they are all, without exception, consuming it. The most massive stars burn brightest and die fastest, exhausting their fuel in millions of years and ending in spectacular supernovae that seed the surrounding space with heavy elements. The smaller stars, the red dwarfs, the most common type of star in the galaxy, burn so slowly and so dimly that they will persist for trillions of years, but they will not persist forever. Even the longest-lived stars will eventually exhaust their fuel and fade. The Sun has approximately 5 billion years of hydrogen fuel remaining. In 5 billion years, it will exhaust its core hydrogen, expand into a red giant, engulf the inner planets, and eventually shed its outer layers, leaving behind a dense, cooling remnant called a white dwarf. The white dwarf will not burn. It will not generate new energy. It will simply cool, over billions and trillions of years, radiating away the heat it accumulated during its active life, growing dimmer and colder until it becomes a black dwarf, a cold, dark, inert ball of degenerate matter, invisible in the darkness of an expanding universe. This fate awaits every star, not the dramatic ones, not the massive stars that end in supernovae and leave behind neutron stars or black holes, but the vast majority of stars, the small and medium ones that make up most of the galaxy's stellar population, will end as white dwarfs, cooling slowly into black dwarfs over timescales that dwarf the current age of the universe. The galaxy will not go dark all at once. It will fade gradually, star by star, over trillions of years, as each stellar furnace exhausts its fuel and goes cold. But it goes deeper, because the fate of the stars is only the beginning of the long thermodynamic story of the universe. Beyond the death of the stars, beyond the cooling of the white dwarfs, beyond the fading of the galaxy's light, there are deeper and stranger processes at work, processes that operate on timescales so vast that the current age of the universe is not even a rounding error in comparison. Processes that will, given enough time, dismantle not just the stars, but the very structure of matter itself. The proton, the fundamental particle at the heart of every atomic nucleus, the building block of every atom of every element in the universe, may not be stable forever. Certain extensions of the standard model of particle physics predict that protons will eventually decay, transforming into lighter particles and radiation over timescales of perhaps 10 to the power of 34 years or longer. If proton decay occurs, then all ordinary matter, every atom, every molecule, every planet, every dead star, will eventually dissolve, not through any violent process, but through the slow, patient, statistical inevitability of quantum decay. One by one, over unimaginable stretches of time, the protons that make up the material universe will cease to exist, leaving behind only radiation and the lightest possible particles. And even if protons do not decay, even if ordinary matter is stable on timescales longer than any current theory predicts, the universe still has a final destination. A destination that is not dramatic, not violent, not explosive, a destination that is, in its own way, more unsettling than any catastrophe, a destination that the laws of thermodynamics have been pointing toward since the first moment of the universe's existence, a destination called heat death. And that is where this descent is ultimately heading, into the cold, dark, silent future of a universe that has run out of gradients, run out of differences, run out of the thermodynamic potential that makes any process, any structure, any event possible. But that final destination requires its own careful approach. It requires understanding not just the emptiness of space, but the nature of energy, the direction of time, and the slow, irreversible process by which the universe moves from a state of high organization and low entropy toward a state of maximum disorder and maximum emptiness. It requires understanding what entropy actually means at cosmic scales, not as an abstract thermodynamic concept, but as a physical reality that is already shaping the future of every star, every galaxy, every black hole, every particle in the observable universe. For now, hold the picture that has been assembled so far, a universe that is mostly empty at the atomic scale, mostly empty at the solar system scale, mostly empty at the galactic scale, dominated by cosmic voids at the largest scales, threaded with invisible dark matter that shapes the structure of the visible world without being part of it, driven apart by dark energy that fills space with an expansive pressure that grows stronger as space grows larger. A universe in which the matter we can see represents 5% of the total energy content, and in which even that 5% is separated by distances so vast that the matter is, for most practical purposes, isolated from itself. This is the universe as it actually is, not the universe of ordinary perception, the warm, full, solid present world of rooms and bodies and morning light, not the universe of the night sky, that beautiful, deceptive projection of depth compressed into a flat field of light, the actual universe, the one that exists at every scale above and below the narrow band of human perception, the one that is, at its heart, an ocean of darkness, with rare, temporary islands of light and structure scattered through it at distances that make the word isolated feel inadequate. And the ocean is getting larger. Every moment, the space between the islands grows. Every moment, the light from the most distant galaxies is redshifted a little further toward invisibility. Every moment, the cosmic horizon draws a little tighter around the local group, excluding a little more of the universe from the set of things we can ever observe or reach. The universe is not static. It is not waiting. It is moving, relentlessly and without pause, in the direction of greater emptiness, greater isolation, greater separation, and it has been doing so for 13.8 billion years, and it will continue doing so for a duration that makes 13.8 billion years look like the first breath of a very long silence. The stars are still burning, for now. The galaxies are still visible, for now. The cosmic web still traces its pattern of filaments and voids across the observable universe, for now. But the word, for now, carries a weight in this context that it does not carry in ordinary life. In ordinary life, for now means something temporary but replaceable, a condition that will change, but that will be followed by other conditions, other structures, other arrangements. In the context of the universe's thermodynamic future, for now means something different. It means before the long, irreversible process of cooling and separation and dissolution has run its course. It means in the brief, bright, improbable window of time when the universe still has enough organized energy to maintain the structures we call stars and galaxies and matter. It means now, while there is still something to see. There is something in the human mind that resists the full weight of these numbers, not through ignorance and not through laziness, but through a kind of deep structural incompatibility between the scale of the cosmos and the scale at which consciousness operates. The brain evolved to track predators across a savanna, to recognize faces, to judge distances measured in meters, to plan across timescales measured in years. It did not evolve to genuinely feel the difference between 1,000,000 light years and 1,000,000,000 light years. It did not evolve to hold the boat as void in its true proportions, or to viscerally understand what it means for space itself to be expanding. These are not failures of intelligence. They are the natural limits of a biological instrument built for a very different purpose than cosmic comprehension. But there is a way through those limits, not by forcing the brain to feel what it cannot feel, but by following the implications of what the numbers actually mean, by tracing the consequences of the emptiness outward, from the scale of atoms to the scale of superclusters, and then asking what kind of universe these facts describe, not what kind of universe we would prefer to inhabit, or what kind of universe our intuitions suggest we inhabit, but what kind of universe the evidence actually points toward. And the evidence points toward something that is, in its broad outlines, deeply strange. A universe in which the visible, tangible, luminous world is a thin and temporary exception to a vast and permanent darkness. A universe in which the forces that build structure are always, in the end, outrun by the forces that dissolve it. To understand why, it helps to understand what structure actually is. Not in the everyday sense, not buildings and bridges and the organized complexity of living things, but in the physical sense. Structure, at the most fundamental level, is a departure from equilibrium. It is a region of space where matter or energy is arranged in a way that is less probable than the surrounding arrangement. A star is structure. It is a concentration of matter so dense that nuclear fusion ignites at its core, producing energy that flows outward against the pressure of gravity, maintaining a dynamic balance that can persist for millions or billions of years. A galaxy is structure. It is a gravitationally bound collection of stars, gas, dust, and dark matter, rotating together, maintaining its organization against the tendency of matter to disperse. A living cell is structure. It is a collection of molecules arranged in a configuration of extraordinary improbability, maintained by a continuous flow of energy that keeps it far from thermodynamic equilibrium. All of these structures, the star, the galaxy, the cell, exist because there are energy gradients available to maintain them. A gradient is a difference, a temperature difference, a density difference, a chemical potential difference. Wherever a gradient exists, energy can flow from the high side to the low side, and that flow can do work, and that work can build and maintain structure. The sun is a gradient, a region of extremely high temperature and density surrounded by the cold vacuum of space. Life on Earth exists because of that gradient, because energy flows from the hot sun across the cold space to the Earth's surface, and that flow of energy can be captured and used to build and maintain the improbable structures we call living things. But gradients do not last forever. They are consumed by the very processes they enable. Every time energy flows from a hot region to a cold region, the gradient between them decreases. Every time a star burns its nuclear fuel, the gradient between the star's core and the surrounding space diminishes slightly. Every time a living thing metabolizes food, the chemical gradient that powered the metabolism is reduced. The universe began with an enormous gradient, an extraordinarily hot, dense, organized state that has been flowing toward equilibrium ever since, and the direction of that flow is irreversible. The second law of thermodynamics does not permit gradients to spontaneously re-establish themselves. Energy flows from hot to cold, from concentrated to dispersed, from organized to disordered, always, without exception, and the universe as a whole is moving in that direction. This is entropy. Not the colloquial version, not simply disorder or messiness, but the precise thermodynamic concept, the measure of the number of ways a system can be arranged at the microscopic level while appearing the same at the macroscopic level. A high entropy state is one with many possible microscopic arrangements. A low entropy state is one with few. The early universe was in an extraordinarily low entropy state, highly organized, highly structured, with enormous gradients available for energy to flow across. The future universe will be in a high entropy state, maximally disordered, maximally dispersed, with no gradients remaining, no energy available to do work, no possibility of maintaining or building any structure at all. The universe is not moving toward this state because something is destroying it. It is moving toward this state because that is what the laws of physics require. The second law of thermodynamics is not a force. It is a statistical inevitability. There are vastly more ways for the universe to be disordered than for it to be ordered, and so, over time, the universe tends toward disorder. Not because disorder is preferred in any meaningful sense, but because it is overwhelmingly more probable. The organized, structured, luminous universe we inhabit is a statistical fluctuation, an improbable arrangement that is slowly, inexorably relaxing toward the most probable arrangement, which is maximum entropy, maximum disorder, maximum emptiness. And the emptiness of space is not separate from this process. It is part of it. The vast cosmic voids, the expanding distances between galaxies, the accelerating separation driven by dark energy, all of these are expressions of the universe's thermodynamic trajectory. The universe is not merely spatially empty, it is thermodynamically emptying. It is moving toward a state in which the energy that currently maintains the gradients, the nuclear fuel in the stars, the gravitational potential energy in collapsing gas clouds, the chemical energy in living things, has been fully dissipated, spread uniformly across an ever-expanding volume of space, leaving no differences, no gradients, no possibility of work or structure or event. But before we arrive at that final state, there is another layer of the universe's architecture that needs to be examined, a layer that is, in some ways, the most unsettling of all, because it is invisible, because it cannot be seen, touched, or directly detected by any instrument currently available to science, and yet it is, by mass, the dominant form of matter in the universe. It is the scaffolding on which everything visible has been built. It is the reason the cosmic web has the structure it has, the reason galaxies formed where they did, the reason the universe looks the way it looks. And we do not know what it is. Dark matter. The name is almost too simple for what it represents. It is not dark in the way that a dark room is dark, not simply the absence of light. It is dark in the sense that it does not interact with light at all. It does not emit light. It does not absorb light. It does not reflect light. It passes through ordinary matter almost without interaction, as if ordinary matter were not there. It is present everywhere, in galaxies, in galaxy clusters, in the vast halos that surround and extend far beyond the visible boundaries of every galaxy, but it is detectable only through its gravitational effects. We know it is there because of what it does to the things we can see. We cannot see it directly. We can only see its shadow. The evidence for dark matter is overwhelming and comes from multiple independent lines of observation. The rotation curves of galaxies were among the first clues. When astronomers measure how fast stars orbit the center of a galaxy, they expect to find that stars farther from the center orbit more slowly, just as the outer planets of the solar system orbit the sun more slowly than the inner ones. This is what Newtonian gravity predicts for a mass concentrated at the center. But what astronomers actually observe is different. Stars in the outer regions of galaxies orbit at roughly the same speed as stars closer to the center, sometimes even faster. The rotation curves are flat, not declining. This means there is more mass in the outer regions of galaxies than the visible stars and gas can account for. There is something else there, something massive and invisible, extending far beyond the visible disk of the galaxy, providing the gravitational pull that keeps the outer stars moving at the speeds they are observed to move. This invisible mass, the dark matter halo, is not a small correction to the visible mass. It is the dominant component. For a typical spiral galaxy like the Milky Way, the dark matter halo contains roughly 5 to 10 times as much mass as all the visible stars and gas combined. The galaxy we see, the luminous disk of stars and nebulae and star-forming regions, is embedded within a much larger, much more massive structure of dark matter that extends far beyond the visible boundaries of the galaxy. The visible galaxy is, in a sense, the tip of an iceberg. The bulk of the mass is invisible, extending into the darkness in every direction, shaping the gravitational environment in which the visible stars and gas move. The gravitational lensing of light provides another line of evidence. When light from a distant galaxy passes near a massive object, a galaxy cluster for example, the gravity of that object bends the light, distorting the image of the background galaxy. By measuring the degree of distortion, astronomers can calculate the total mass of the lensing object, and consistently, the mass inferred from gravitational lensing is far greater than the mass that can be accounted for by the visible matter in the lensing object. The difference is dark matter, invisible mass that is bending the light just as effectively as visible mass would, but without emitting or absorbing any of it. The cosmic microwave background, the faint afterglow of the Big Bang, the oldest light in the universe, also bears the imprint of dark matter. The tiny temperature fluctuations in the cosmic microwave background encode information about the density and distribution of matter in the early universe, and the pattern of those fluctuations is consistent with a universe in which dark matter is the dominant form of matter, outweighing ordinary matter by roughly 5 to 1. The structure of the cosmic web, the filaments, the clusters, the voids, matches the predictions of models that include dark matter and does not match the predictions of models that do not. Dark matter is not a hypothesis invented to explain one anomaly. It is a conclusion demanded by multiple independent observations, each pointing to the same invisible presence. And this leads to something more disturbing. Because if dark matter is real, and the evidence strongly suggests it is, then the universe we can see is not the universe as it actually is. The visible universe, the luminous universe of stars and galaxies and nebulae, is a thin, bright layer painted on top of a much larger, much more massive, completely invisible structure. The dark matter halos of galaxies, the dark matter filaments of the cosmic web, the dark matter that permeates every galaxy cluster. All of this invisible mass is the true skeleton of the cosmos. The visible matter is not the structure, it is the decoration on the structure. It is the luminous trace left by ordinary matter as it fell into the gravitational wells carved by dark matter in the early universe. Think about what this means for the picture of the universe that has been assembled so far. We began with the observation that the universe is mostly empty, that matter is rare, that the distances between objects are vast, that the cosmic voids dominate the large-scale structure. And this is true for visible matter. But dark matter is distributed differently. It is not concentrated in the same way as visible matter. It does not collapse into stars or planets. It does not form the dense luminous concentrations that we call galaxies in the ordinary sense. It forms halos, extended, diffuse structures that surround and permeate the visible galaxies, extending far beyond their luminous boundaries into the surrounding space. So the universe is not simply empty space with rare islands of visible matter. It is empty space with rare islands of visible matter, embedded within a more pervasive, invisible structure of dark matter. The dark matter is everywhere that the visible matter is, and also in many places where the visible matter is not. It fills the halos of galaxies, the spaces between galaxies within clusters, the filaments of the cosmic web. It is the dominant gravitational presence in the universe, and it is completely invisible to every form of electromagnetic observation. We live inside it. We move through it. We are surrounded by it at every moment, and we cannot detect it directly. This invisibility is not a temporary limitation of our technology. It is a fundamental property of dark matter, whatever it turns out to be. Dark matter does not interact with the electromagnetic force, the force that governs the behavior of light and the interactions between charged particles. This means it cannot emit, absorb, or scatter photons of any wavelength. It is invisible not because it is too faint or too distant, but because it simply does not participate in the electromagnetic interactions that make things visible. It exists in a kind of parallel layer of reality, interacting with ordinary matter only through gravity, shaping the universe from the inside of a darkness that no telescope can penetrate. We do not know what dark matter is made of. This is not a minor gap in our knowledge. It is one of the most significant open questions in all of physics. The leading candidates are hypothetical particles, weakly interacting massive particles, or WIMPs, axions, sterile neutrinos, and others. But decades of increasingly sensitive experiments have failed to directly detect any of them. The dark matter is there. Its gravitational effects are unmistakable, but its identity remains unknown. We are surrounded by the dominant form of matter in the universe, and we cannot say what it is. And alongside dark matter, filling the rest of the universe's energy budget, is dark energy, that even stranger, even more pervasive presence that is driving the accelerating expansion of space. If dark matter is the invisible skeleton of the cosmos, dark energy is the invisible breath that is slowly pulling that skeleton apart. Dark matter holds structures together. Dark energy pushes them apart. And over cosmic time, dark energy is winning. The competition between dark matter and dark energy is not a battle in any dramatic sense. It is a slow, patient, thermodynamic process playing out over billions of years. On small scales, within galaxies, within galaxy clusters, gravity is strong enough to hold structures together against the expansive pressure of dark energy. The Milky Way will not be torn apart by dark energy. The local group will not be dispersed by it. Gravity on these scales is sufficient to maintain the gravitational bonds that hold these structures together. But on larger scales, between galaxy clusters, between superclusters, dark energy dominates. The expansion of space is carrying these structures apart faster than gravity can pull them back together. And the acceleration of that expansion means the separation is increasing over time. The result is a universe that is simultaneously holding together at small scales and falling apart at large scales. Within the local group, the Milky Way and Andromeda are actually approaching each other. They will collide and merge in approximately 4.5 billion years, forming a new, larger elliptical galaxy. Within galaxy clusters, the member galaxies are gravitationally bound and will remain so. But between clusters, between superclusters, the expansion of space is creating an ever-growing gulf that no gravitational force can bridge. The universe is fragmenting at its largest scales, breaking into isolated gravitational islands that will eventually lose all contact with each other. This fragmentation is already underway. It has been underway for billions of years, and it will continue with increasing completeness for billions and trillions of years to come. The universe is not exploding. It is not collapsing. It is separating, quietly, steadily, without drama or announcement. The largest structures in the cosmos are drifting apart, carried by the expansion of space into a future of increasing isolation and decreasing connectivity. The cosmic web, which today traces the large-scale structure of the universe in its filaments and clusters and voids, will eventually dissolve, not because the matter in it disappears, but because the expansion of space will stretch the filaments beyond the point where gravity can maintain them, leaving behind isolated clusters and groups, each one an island in an expanding ocean of dark energy. But it goes deeper, because dark energy does not merely separate structures. It also affects what those structures can observe and interact with. As the expansion accelerates, the cosmic horizon, the boundary beyond which light can never reach us, is shrinking relative to the total size of the universe. More and more of the universe is being carried beyond the horizon, into a region from which no signal can ever return. The universe is not merely becoming more isolated in a spatial sense, it is becoming more isolated in an informational sense. The amount of the universe that is, in principle, accessible to any observer is decreasing over time. The observable universe is shrinking, not because the universe itself is shrinking, but because the expansion is outpacing the ability of light to cross the growing distances. In the very far future, in a time so distant that it makes the current age of the universe look like an instant, the only galaxies visible in the night sky of any observer will be the galaxies of their own local gravitational group. Everything else will have receded beyond the horizon, redshifted into invisibility, their light stretched by the expansion of space until it carries no detectable energy. An observer in the far future looking up at the night sky will see a small collection of nearby galaxies, the remnants of the local group, merged into a single large elliptical galaxy, surrounded by absolute darkness. Not the darkness of a moonless night, with its background of distant stars and galaxies. Absolute darkness, a sky in which the universe beyond the local island is completely invisible, completely unreachable, completely gone from the observable world. And that future observer, if they existed, would have no way of knowing that the universe was once larger, once more connected, once filled with the light of 2 trillion galaxies spread across a cosmic web of filaments and voids. The evidence would be gone. The light from those distant galaxies would have long since passed beyond the horizon. The cosmic microwave background, that faint afterglow of the Big Bang that tells us so much about the early universe, would have been redshifted to wavelengths so long that it would be undetectable. The universe's own history would be hidden from any observer born late enough into the cosmic timeline. The evidence for the Big Bang, for the cosmic web, for the existence of other galaxies beyond the local group, all of it would be inaccessible. The universe would appear to a sufficiently late observer to be nothing more than a single island of matter in an infinite, featureless, expanding void. This is one of the most quietly devastating implications of dark energy and accelerating expansion. We happen to live at a time when the universe is still young enough and the expansion still slow enough that we can observe the cosmic web, measure the cosmic microwave background, detect the signatures of the Big Bang, and reconstruct the history of the universe from its earliest moments to the present. We live in a privileged window of cosmic time, a window that is already closing, and that will eventually close completely. The knowledge we have accumulated about the universe's origin and large-scale structure is knowledge that will become, in the far future, permanently inaccessible, not because it will be forgotten, but because the evidence for it will have physically disappeared beyond the cosmic horizon. The universe is not merely empty, it is becoming epistemically empty, a place where the information needed to understand its own history is being systematically erased by the expansion of space. The cosmos is not just separating its structures, it is separating itself from its own past, carrying the evidence of its origin beyond the reach of any future observer. This is a kind of cosmic amnesia, written into the laws of physics, operating on timescales of trillions of years, and it is as irreversible as the second law of thermodynamics. And yet, even the accelerating expansion, the shrinking horizon, the cosmic amnesia, is not the deepest layer of the universe's trajectory toward emptiness, because the expansion of space and the isolation of gravitational islands describes the large-scale fate of the universe's structure. It describes what happens to the arrangement of galaxies over cosmic time. But within those isolated islands, within the gravitationally bound remnants of the local group and other galaxy clusters, the story continues. The stars continue to burn, the matter continues to evolve, and the thermodynamic processes that are driving the universe toward maximum entropy continue to operate on smaller scales with the same patient inevitability. Consider the stars again. The Milky Way currently contains somewhere between 100 billion and 400 billion stars in various stages of their life cycles. Some are young, recently formed from collapsing clouds of gas and dust, burning bright and hot with the energy of nuclear fusion. Some are middle-aged, like the Sun, steadily converting hydrogen to helium in their cores, maintaining the balance between gravity and radiation pressure that defines the main sequence of stellar evolution. Some are old, having exhausted their core hydrogen and expanded into red giants, or having already shed their outer layers and collapsed into white dwarfs. And some are the remnants of the most massive stars, neutron stars and black holes, the densest objects in the universe, the endpoints of the most dramatic stellar deaths. All of these stars, in all of their stages, are consuming something. They are consuming the nuclear fuel that was present in the gas clouds from which they formed. Hydrogen, primarily the most abundant element in the universe, the legacy of the Big Bang. And the supply of that fuel is finite. The galaxy contains a finite amount of hydrogen. Some of it is locked up in stars, being consumed by fusion. Some of it is in the interstellar medium, available to form new stars. Some of it has already been processed through stars and returned to the interstellar medium as heavier elements. But the total amount is fixed, and it is being consumed at a rate that, over cosmic time, will exhaust it. The rate of star formation in the Milky Way has already been declining for billions of years. The galaxy formed most of its stars in the first few billion years of its existence, when the interstellar medium was rich with the primordial hydrogen and helium of the Big Bang. As that gas has been consumed, locked up in stars, converted to heavier elements, blown out of the galaxy by stellar winds and supernovae, the rate of new star formation has declined. The galaxy is not as productive as it once was. It is aging. The brilliant star-forming spiral arms that define its appearance today are a feature of its middle age, not its permanent character. In the far future, as the remaining gas is consumed and the rate of star formation drops to zero, the galaxy will stop making new stars entirely. The existing stars will continue to burn, each one on its own timeline, but no new ones will be born to replace them. This is the beginning of the stellar era's end. Not a sudden darkness, but a gradual dimming. A slow, star-by-star fading that will play out over trillions of years. The most massive stars will die first, in supernovae that briefly outshine entire galaxies, leaving behind neutron stars and black holes. The medium-mass stars, like the Sun, will exhaust their fuel over billions of years, expanding into red giants and then collapsing into white dwarfs. The smallest stars, the red dwarfs, which burn so slowly and so dimly that they are barely visible to the naked eye, will persist for trillions of years, outlasting all other stellar types by enormous margins. But even they will eventually exhaust their fuel and fade. The last stars to die will be the smallest red dwarfs, burning their hydrogen so frugally that they can persist for perhaps 10 trillion years, roughly 1,000 times the current age of the universe. When the last red dwarf finally exhausts its fuel and fades, the galaxy will go dark. Not immediately. The white dwarfs will still be cooling. The neutron stars will still be spinning. The black holes will still be present. But the era of starlight will be over. The galaxy that once blazed with the light of hundreds of billions of nuclear furnaces will be a cold, dark collection of stellar remnants, drifting through the expanding universe in a darkness that no new star will ever break. But it gets worse, because the death of the stars is not the end of the story. It is not even close to the end. The timescales involved in the subsequent evolution of the universe are so vast that the stellar era, the entire period from the formation of the first stars to the death of the last red dwarf, spanning perhaps 100 trillion years, will eventually come to seem like a brief bright flash at the beginning of a much longer, much darker history. After the stars are gone, the universe enters what cosmologists call the degenerate era, a period dominated by the cold remnants of stellar evolution. White dwarfs, neutron stars, and black holes will be the primary inhabitants of the universe during this era, which may last for 10 to the power of 40 years or longer. The white dwarfs will continue to cool, radiating away their residual heat over unimaginable timescales, growing dimmer and colder until they become black dwarfs, objects so cold that they emit no detectable radiation at all. The neutron stars will spin down, their rotation slowing as they radiate away their rotational energy. The black holes will persist, their gravity unchanged, their event horizons intact, waiting. And the black holes will be waiting for something that was predicted by Stephen Hawking in 1974, and that represents one of the most remarkable intersections of quantum mechanics and general relativity in all of theoretical physics. Hawking radiation, the process by which black holes, despite their reputation for consuming everything and releasing nothing, slowly evaporate over time. Not through any conventional emission process, but through a quantum mechanical effect at the event horizon, where the uncertainty principle allows pairs of virtual particles to briefly exist, with one particle falling into the black hole and the other escaping as real radiation. Over time, this process causes the black hole to lose mass, slowly, imperceptibly slowly, until it has evaporated entirely. The timescale for black hole evaporation depends on the mass of the black hole. A stellar mass black hole, the remnant of a massive star, would take approximately 10 to the power of 67 years to evaporate through Hawking radiation. A supermassive black hole, like the one at the center of the Milky Way, which has a mass of roughly 4 million solar masses, would take approximately 10 to the power of 87 years. These are numbers so large that they resist any meaningful comparison. The current age of the universe is approximately 1.4 times 10 to the power of 10 years. The evaporation time of a supermassive black hole is 10 to the power of 77 times longer than the current age of the universe. It is a duration so vast that every other timescale in the universe's history, the stellar era, the degenerate era, the entire period from the Big Bang to the death of the last star, is compressed into an infinitesimal fraction of it. But the black holes will evaporate, given enough time, and the universe has enough time and more. Even the most massive black holes will eventually radiate away their mass entirely, ending in a final burst of high-energy radiation and leaving behind nothing but the expanding void. When the last black hole evaporates, the universe will contain no large concentrations of mass anywhere. No stars, no planets, no white dwarfs, no neutron stars, no black holes. Only the cold, diffuse remnants of everything that once existed, a thin, uniform gas of the lightest possible particles, photons and neutrinos, spread across an ever-expanding volume of space, growing colder and more dilute with every passing moment. This is the heat death, not a dramatic ending, not an explosion or a collapse or a final catastrophic event. Just the slow, patient thermodynamic completion of a process that began at the moment of the Big Bang, the gradual dissipation of all gradients, the equalization of all temperatures, the dispersal of all concentrations of energy into a uniform, featureless, maximally entropic state. A universe in which nothing happens because nothing can happen. A universe in which there are no differences left to drive any process, no gradients left to do any work, no structures left to maintain any organization. A universe that has reached thermodynamic equilibrium, the state of maximum entropy, maximum disorder, maximum emptiness. And in that state, the universe will persist, not as a place where things happen, but as a place where things no longer can. An infinite, expanding, cold, dark, featureless void, containing only the most diffuse possible distribution of the most fundamental possible particles, growing colder and more dilute as the expansion of space continues to stretch it. No light, no heat, no structure, no event, no information processing of any kind, no possibility of consciousness, or life, or observation, or meaning. Just the void expanding forever, in a silence so complete that the word silence is inadequate, because silence implies the absence of sound in a place where sound could exist. This is the absence of everything in a place where nothing can exist. There is a particular quality to the silence that follows a very large number, not the silence of incomprehension, not the blank, defensive quiet of a mind that has simply refused to engage, but the silence of a mind that has engaged, that has followed the logic as far as it goes, and that has arrived somewhere it did not expect to be, somewhere without handholds. Somewhere where the ordinary tools of reassurance, the sense that things will continue, that the future holds more of what the present contains, that existence is a stable condition rather than a temporary one, have quietly stopped working. That is the silence that the heat death of the universe produces when it is genuinely understood rather than merely acknowledged as an abstract fact. But there is a step between the present and that final silence that deserves careful attention, because the heat death is not simply a distant endpoint that the universe will eventually reach after a long journey. It is the destination toward which every process in the universe is already moving, right now, at every scale, in every structure, in every interaction between matter and energy. The arrow of time, the irreversible directionality that distinguishes the past from the future, that makes a broken glass different from an assembling one, that makes aging different from growing younger, is the arrow that points toward maximum entropy. And it is pointing there continuously without pause in everything that happens. Every star that burns is moving the universe closer to heat death. Every chemical reaction, every biological process, every thought that occurs in a biological brain, all of these are entropy-increasing events. They are all processes in which organized low-entropy energy, is converted into disorganized, high-entropy heat. Life itself, for all its extraordinary complexity and improbability, is an entropy-generating process. Living things take in low-entropy energy, sunlight, chemical energy, and food, and release high-entropy heat into the environment. They build local order at the cost of global disorder. They are, in thermodynamic terms, engines for accelerating the universe's approach to equilibrium. This is not a condemnation of life. It is simply a description of what life is, in thermodynamic terms. Life is a process that exploits gradients, that captures the energy flowing from high-entropy states to low-entropy states, and uses it to build and maintain improbable structures. It is extraordinarily good at this. The complexity of a living cell, the sophistication of a nervous system, the richness of a conscious mind, these are among the most improbable structures in the known universe, maintained against the thermodynamic tide by a continuous flow of energy. But the flow of energy that maintains them is itself a gradient-consuming process, and the gradients it consumes are finite. The sun will not burn forever. The chemical energy in food ultimately derives from sunlight, which ultimately derives from the nuclear fuel in the sun's core, which is being consumed at a rate of approximately 600 million tons of hydrogen per second. 600 million tons of hydrogen per second. This is the rate at which the sun is converting its nuclear fuel into energy, into the light and heat that make life on Earth possible. It is an enormous rate by any human standard, and yet the sun contains enough hydrogen to sustain this rate of fusion for approximately another 5 billion years. 5 billion years is a long time. It is longer than the Earth has existed. It is longer than the entire history of life on this planet. But it is finite. It will end. And when it ends, the gradient that has powered every living thing on Earth for the past 4 billion years will be gone. But it goes deeper, because the sun's eventual death is not simply the end of life on Earth. It is one instance of a universal process, the exhaustion of stellar fuel, that is playing out across every star and every galaxy in the observable universe. Every star is a finite resource. Every star is consuming its nuclear fuel at a rate that will eventually exhaust it. The universe's supply of hydrogen, the fuel that powers stellar fusion, is not being replenished. It was created in the first few minutes after the Big Bang, in a process called Big Bang nucleosynthesis, and the amount created then is essentially the total amount available for the entire future history of the universe. Some of it has already been consumed. Some of it has been converted into heavier elements by stellar nucleosynthesis, and is no longer available for fusion in the same way. The supply is finite, and it is being drawn down, star by star, galaxy by galaxy, across the entire observable universe. The universe is running out of fuel, not immediately, not on any timescale that is relevant to human life, or to the history of civilization, or even to the biological history of the Earth. But on cosmic timescales, the depletion of stellar fuel is a real and ongoing process, and its endpoint is a universe in which no star burns, no nuclear fusion occurs, and no new energy is available to maintain any structure against the thermodynamic tide. And this leads to something more disturbing, because the exhaustion of stellar fuel is not the only process depleting the universe's capacity for structure and event. There is also the question of what happens to the matter itself, not just the energy it contains, but the physical structure of the particles that compose it. And here, the physics becomes genuinely strange, because the stability of ordinary matter on very long timescales is not guaranteed. The proton, as mentioned earlier, may be unstable. The standard model of particle physics does not predict proton decay, but many extensions of the standard model, grand unified theories that attempt to unify the strong, weak, and electromagnetic forces, do predict it, on timescales of roughly 10 to the power of 34 years or longer. If protons decay, then all ordinary matter, every atom of every element, every molecule of every compound, every planet, every dead star, every black dwarf, will eventually dissolve. Not through any violent process, but through the slow, statistical inevitability of quantum decay. Each proton, given enough time, will transform into a positron and a neutral pion, which will itself quickly decay into photons. The matter will become radiation. The radiation will disperse, and the universe will be left with one less atom, one less molecule, one less fragment of structure. Multiply this process across every proton in the observable universe, approximately 10 to the power of 80 protons, and the result is a universe in which all ordinary matter has been converted to radiation over a timescale of perhaps 10 to the power of 40 years. Every planet, every asteroid, every white dwarf, every neutron star, every black dwarf, all of it dissolved by the patient statistical process of proton decay, leaving behind only photons and the lightest possible particles, dispersing through an ever-expanding void. Even if protons do not decay, even if ordinary matter is stable on timescales longer than any current theory predicts, there are other processes that will eventually dismantle the structures of matter. Quantum tunneling, for example, allows particles to cross energy barriers that classical physics would consider impassable. Over sufficiently long timescales, quantum tunneling can cause atoms in a solid to rearrange themselves, allowing matter to slowly flow and reorganize even at temperatures near absolute zero. Given enough time, timescales of 10 to the power of 65 years or more, even the cold inert black dwarfs will eventually rearrange their internal structure through quantum tunneling, collapsing into denser configurations, or, in some theoretical scenarios, tunneling into iron, the most thermodynamically stable nuclear configuration, and eventually collapsing into neutron stars or black holes through the slow accumulation of quantum rearrangements. The universe, in other words, does not simply run down. It actively dismantles itself through a variety of processes operating on different timescales, each one contributing to the overall trend toward maximum entropy and minimum structure. The stars burn out, the white dwarfs cool, the protons decay, or the quantum tunneling rearranges the matter. The black holes evaporate, and at each stage, the universe becomes a little emptier, a little colder, a little more uniform, a little closer to the featureless equilibrium that is its ultimate destination. There is a concept in information theory that is relevant here, and it adds another dimension to the picture. Information, in the technical sense, is a measure of the distinguishability of states, the degree to which one arrangement of a system can be told apart from another. A highly organized system contains a great deal of information, because its specific arrangement is one of a very small number of possible arrangements. A highly disordered system contains very little information, because its arrangement is one of an enormous number of essentially equivalent arrangements. As entropy increases, information decreases. As the universe moves toward maximum entropy, it moves toward minimum information, toward a state in which there is nothing to distinguish one region of space from another, nothing to record, nothing to transmit, nothing to process. The loss of information is not merely a thermodynamic abstraction, it has physical consequences. In a universe approaching maximum entropy, the conditions necessary for information processing, for computation, for memory, for the kind of organized physical processes that underlie consciousness, become increasingly unavailable, not because information is forbidden, but because the physical substrates that support information processing require energy gradients to operate, and energy gradients are precisely what the universe is running out of. A mind requires a gradient. A thought requires a gradient. The difference between a living brain and a dead one is, at the most fundamental level, a thermodynamic difference. The living brain is far from equilibrium, maintained by a continuous flow of energy, while the dead brain has reached equilibrium with its surroundings. In the far future, as the universe approaches maximum entropy, the conditions that support any form of information processing will become increasingly rare and eventually impossible, not because the laws of physics change, but because the physical conditions necessary for those laws to produce complex organized behavior will no longer exist. The universe will not become a place where consciousness is forbidden. It will become a place where consciousness is thermodynamically impossible, where there are no gradients left to power the processes that give rise to it. This is perhaps the most quietly devastating aspect of the universe's thermodynamic trajectory. Not the death of the stars, not the evaporation of the black holes, not even the dissolution of matter itself, but the permanent, irreversible end of the conditions that make experience possible. The universe will not merely become empty of matter, it will become empty of the possibility of experience, empty of the possibility of observation, empty of the possibility of any process that could be called, in any meaningful sense, an event. It will become a place where nothing happens, not because something prevents it, but because there is nothing left that could make it happen. And yet, even in this bleak thermodynamic future, there is one more layer to consider, one more aspect of the universe's trajectory that adds a final strange dimension to the picture. It concerns not the fate of matter or energy, but the fate of space itself, the fabric of the cosmos, the medium in which all of this emptiness exists. Because space, in the framework of general relativity, is not a passive container. It is a dynamic entity. It curves in response to mass and energy. It expands under the influence of dark energy, and its future behavior, on the longest possible timescales, is not entirely certain. The current best understanding of dark energy treats it as a cosmological constant, a fixed property of space that does not change over time. Under this assumption, the expansion of the universe will continue to accelerate indefinitely, and the universe will approach the heat death asymptotically, growing colder and more dilute forever, without ever quite reaching absolute zero or absolute emptiness. But there are other possibilities. Some theoretical models suggest that dark energy is not a constant, but a dynamic field, one that could change over time, potentially growing stronger or weaker as the universe evolves. If dark energy grows stronger over time, the consequences could be far more dramatic than the gentle heat death described by the cosmological constant model. In the most extreme version of this scenario, called the Big Rip, dark energy grows so strong that it eventually overcomes not just the gravity-holding galaxy clusters together, but the gravity-holding individual galaxies together, then the gravity-holding solar systems together, then the electromagnetic forces holding atoms together, and finally the nuclear forces holding atomic nuclei together. In the Big Rip, the expansion of space accelerates without limit, tearing apart every structure in the universe, from the largest galaxy cluster to the smallest atomic nucleus, in a finite amount of time. The universe does not fade quietly into heat death. It is torn apart, structure by structure, in a final violent expansion that ends with the fabric of space itself being stretched to infinity. The Big Rip is not the most likely scenario, based on current observations. The data is more consistent with a cosmological constant, with dark energy that remains roughly constant over time, leading to the gentle, asymptotic heat death rather than the violent tearing. But the possibility of the Big Rip is a reminder that the universe's future is not entirely settled. The nature of dark energy, that 68% of the universe's energy content that we cannot directly detect or fully understand, remains one of the deepest open questions in cosmology. And the answer to that question will determine, in the most literal sense, the ultimate fate of everything. But whether the universe ends in the quiet heat death or the violent Big Rip or some other scenario that current physics has not yet imagined, the broad outlines of the story are the same. The universe began in a state of extraordinary organization and low entropy. It has been moving toward higher entropy ever since. The structures it has built along the way, like the galaxies, the stars, the planets, the living things, are temporary departures from the thermodynamic trend maintained by the exploitation of finite energy gradients. Those gradients are being consumed. The structures are temporary. The trend is irreversible, and the destination, whatever its precise character, is a universe that is emptier, colder, darker, and more uniform than the one we inhabit today. This is the universe's story, told from the perspective of thermodynamics, and it is a story that has been unfolding since the first moment of the Big Bang, in every process, at every scale, in every corner of the observable cosmos. It is not a story that was imposed on the universe from outside. It is not a story that could have been different, given the laws of physics as they are. It is the story that the laws of physics require, the inevitable consequence of a universe that began in a low entropy state and is governed by the second law of thermodynamics. And here is where the story becomes personal, because you are part of it, not as a passive observer, but as a participant. Every process in your body, every heartbeat, every breath, every electrochemical signal in your nervous system is an entropy-generating event. You are, in thermodynamic terms, a local and temporary reduction in entropy, maintained by a continuous flow of energy from the sun, through the food you eat, through the metabolic processes of your cells. You are a structure. You are a departure from equilibrium. You are one of the universe's improbable, temporary, extraordinarily complex exceptions to the rule of disorder, and you are aware of it. This is the most remarkable thing. Not that you exist. The universe has produced many structures, many departures from equilibrium, many improbable arrangements of matter and energy, but that you are aware of your existence, that you can contemplate the universe's thermodynamic trajectory, that you can understand, at least in outline, the story of how the cosmos began, how it evolved, and where it is going, that you can sit in a room, feel the floor beneath you, look up at the night sky and know, not just sense, but actually know, that the stars you are looking at are burning their finite fuel, that the galaxies beyond them are receding into an expanding void, that the universe you inhabit is moving inexorably and without pause toward a state of maximum emptiness and minimum structure. This awareness is extraordinary. It is also, in the context of the universe's thermodynamic future, almost impossibly fragile. The conditions that make consciousness possible, the energy gradients, the organized structures, the improbable arrangements of matter that give rise to nervous systems and brains and the capacity for experience, are temporary. They exist now, in this brief window of cosmic time, because the universe is still young enough and energetic enough to maintain them. But they will not exist forever. The window will close, the gradients will be consumed, the structures will dissolve, and the awareness that currently exists in the universe, whatever form it takes, wherever it is located, will eventually cease, not because it is destroyed, but because the physical conditions that support it will no longer be available. The universe does not care about this. The universe does not care about anything. It is not indifferent in the way that a person can be indifferent, with the implication that indifference is a choice, that caring was possible and was declined. The universe is indifferent in a more absolute sense. It is a physical system governed by laws that have no provision for caring, no mechanism for preference, no capacity for concern. The second law of thermodynamics does not make exceptions for consciousness. The expansion of space does not slow down for observers. The exhaustion of stellar fuel does not pause for the civilizations that depend on it. The universe proceeds according to its laws, and its laws lead where they lead, and where they lead is toward emptiness. But it gets worse, because there is one final aspect of the universe's trajectory that has not yet been fully examined. One final implication of the emptiness and the expansion and the thermodynamic trend that adds a last, strange note to the picture. It concerns not the fate of the universe's matter or energy, but the fate of the universe's reachability, the degree to which the different parts of the universe can, in principle, affect each other. And the answer, as the expansion continues and the horizon shrinks, is that the universe is becoming less and less connected, not just in the sense that the distances between structures are growing, but in the deeper sense that the causal connections between different regions of space, the ability of events in one region to influence events in another, are being severed, one by one, as the expansion carries regions beyond each other's horizons. In the very early universe, everything was causally connected to everything else. The universe was small enough and the expansion slow enough that light could travel between any 2 points in a reasonable time. As the universe expanded, the causal connections between distant regions were stretched, but not yet severed. Today, we can observe galaxies that are billions of light years away, and we can, in principle, send signals to them, though those signals would take billions of years to arrive, and the galaxies would have moved further away in the meantime. But the causal connection still exists in principle. The universe is still, in some meaningful sense, a single connected system. In the far future, this will no longer be true. As the expansion accelerates, the causal connections between the local group and the rest of the universe will be permanently severed. No signal sent from the local group will ever reach the galaxies beyond the horizon. No signal from those galaxies will ever reach the local group. The universe will have fragmented into causally disconnected regions, islands of matter and energy that can never again influence each other, that exist in a state of permanent, absolute isolation. Not the isolation of distance, which can in principle be crossed given enough time, but the isolation of causal disconnection, which cannot be crossed by any means, ever. This is the final form of cosmic emptiness. Not the emptiness of space between atoms or between planets or between stars or between galaxies, but the emptiness of causal disconnection, the state in which the universe has fragmented into isolated regions that are, for all physical purposes, separate universes, each one alone, each one unable to know that the others exist, each one proceeding toward its own thermodynamic equilibrium in a silence that is not merely the absence of sound, but the absence of any possible communication, any possible connection, any possible shared experience. The universe began as a single, connected, extraordinarily hot and dense system. It will end, if end is even the right word for a process that may continue forever, as a collection of causally disconnected, thermodynamically exhausted, maximally empty regions of expanding space, each one containing nothing but the most diffuse possible distribution of the most fundamental possible particles, growing colder and more dilute forever, in a silence so complete that it makes the silence between the stars seem like noise. This is where the descent leads. This is what the emptiness reveals when it is followed all the way to its conclusion. Not a universe that is merely large or merely old or merely cold. A universe that is, at its deepest level, a system in the process of becoming permanently, irreversibly, absolutely nothing. Not nothing in the sense of non-existence. The space will still be there. The particles will still be there. The laws of physics will still be operating. but nothing in the sense of no structure, no gradient, no event, no information, no experience, no connection. A universe that has exhausted its capacity for anything to happen. And the matter, the 5%, the thin, improbable film of structure that includes every star, every planet, every living thing, every thought that has ever occurred in the history of the cosmos, will have played its role and dissolved, not dramatically, not with a final explosion or a last great event, but quietly, gradually, particle by particle, gradient by gradient, structure by structure, over timescales so vast that the entire history of the universe from the Big Bang to the present is a rounding error. The matter will have been, briefly, and then it will not be, and the universe will continue, empty and expanding and indifferent, for a duration that has no meaningful end. There is a strange comfort that some people find in the scale of these timescales. The heat death is so far in the future, the evaporation of the last black hole so incomprehensibly distant that it seems irrelevant to any concern that could matter to a human life. And in a practical sense, this is true. The thermodynamic fate of the universe has no bearing on what you will do tomorrow, or next year, or in the entire span of your life. The stars will still be burning, the galaxies will still be visible, the cosmic web will still be tracing its pattern of filaments and voids across the observable universe. The world will still feel full and present and real, but the comfort is also a kind of evasion, because the thermodynamic fate of the universe is not merely a distant future event. It is the direction in which the universe is currently moving, right now, at every scale, in every process. The entropy is increasing now. The expansion is accelerating now. The distant galaxies are receding beyond the horizon now, one by one, their light redshifting toward invisibility. The stars are consuming their fuel now. The gradients are being depleted now. The universe is not waiting for some future moment to begin its journey toward emptiness. It is already on that journey. It has always been on that journey. And every moment that passes is a moment in which the universe has moved a little further along it. The room you are sitting in is part of this process. The air you are breathing is part of this process. The light coming through the window, the warmth of the sun on your skin, the electrochemical activity in your brain that is processing these words, all of it is part of the universe's thermodynamic trajectory. All of it is entropy being generated. All of it is gradients being consumed. All of it is the universe moving, in its patient and irreversible way, toward the state of maximum emptiness that is its ultimate destination. And you are aware of this. You are, as far as we know, one of the universe's rare and temporary arrangements of matter that is capable of being aware of anything at all. You are a structure that can contemplate its own impermanence, that can understand the thermodynamic context in which it exists, that can look out at the night sky and know what it is looking at, not just stars, but the brief, bright, temporary exceptions to the universe's overwhelming preference for darkness and emptiness and cold. This awareness does not change the physics. It does not slow the expansion, or replenish the stellar fuel, or reverse the arrow of entropy. But it is, in its own way, one of the most remarkable things in the observable universe. A collection of atoms, themselves mostly empty space, themselves temporary arrangements of particles that will eventually dissolve, that has organized itself into a structure capable of understanding its own context, capable of tracing the descent from the familiar to the cosmic, capable of sitting with the full weight of what the universe actually is, rather than retreating into the comfortable illusion of a world that is solid and full and permanent. And yet the awareness itself raises a question that the physics cannot answer. Not a question about the mechanics of the universe, not a question about dark energy or entropy or the timescale of proton decay, but a question about what it means that the universe has, in at least one place, at least once, produced something capable of asking questions about itself. The universe did not need to do this. The laws of thermodynamics do not require consciousness. The second law does not demand that entropy-generating systems be aware of what they are doing. The expansion of space does not need observers to proceed. And yet here, on this small rocky planet orbiting this ordinary star, in the outer regions of this unremarkable spiral galaxy, the universe has arranged a small amount of its matter into a configuration that can look outward and inward simultaneously, that can trace the structure of the cosmos from the inside of an atom to the edge of the observable universe, and that can feel, however imperfectly, the weight of what it finds. This is not a reason for comfort. It is not a resolution of the existential tension that the universe's true proportions produce. It is simply a fact, one more fact in a long sequence of facts, each one stranger and more unsettling than the last. The universe is mostly empty. The matter within it is temporary. The structures built from that matter are thermodynamically doomed. The expansion of space is severing the causal connections between those structures. And somewhere within all of this lies within the vast, cold, expanding, entropy-increasing cosmos, there is awareness. Brief, local, improbable, and entirely without cosmic significance in any physical sense, but present. For now, return to the room. Return to the floor beneath you, the walls around you, the ceiling above you. Return to the morning light and the glass of water and the folded piece of clothing on the chair. These things are still here. They have not changed. The floor is still solid. The walls still hold their positions. The light still falls through the window at the same angle it always has. Nothing about the room has been altered by the descent that has just been made. From the atom, to the solar system, to the galaxy, to the cosmic web, to the expanding void, to the thermodynamic future of a universe trending toward maximum emptiness. But something has changed, not in the room, in the way the room is perceived. The floor that felt solid now carries the knowledge of its own atomic emptiness. The vast cathedral spaces inside every atom of every molecule of every compound in the material beneath your feet. The walls that felt permanent now carry the knowledge of their own thermodynamic impermanence. The slow, patient process by which every structure in the universe is moving toward dissolution. The light coming through the window now carries the knowledge of its source. A star consuming its finite fuel at 600 million tons per second, burning through the hydrogen that was created in the first minutes after the Big Bang, moving toward the day when the fuel runs out and the light stops. The room is the same. The perception is different, and the difference is not a loss exactly, though it has loss as texture. It is more like the difference between looking at a landscape and knowing nothing about it, and looking at the same landscape knowing that it was shaped by glaciers, that the rock beneath it is billions of years old, that the soil is the accumulated product of millions of years of biological activity, that the trees are organisms with their own evolutionary history stretching back hundreds of millions of years. The landscape does not become less beautiful when you know these things, but it becomes more complex, more layered, more weighted with time and process and the slow, patient work of physics and chemistry and biology, operating across scales that dwarf any individual human life. The universe is like that landscape. It does not become less remarkable when its true proportions are understood, but it becomes something different from what it appeared to be. It becomes a place where the familiar solidity of things is revealed as a temporary arrangement of forces operating across emptiness, where the apparent fullness of the world is revealed as a perceptual artifact, a useful, necessary, biologically constructed interface between consciousness and a reality that is, at nearly every scale, composed primarily of nothing, where the stars that seem to crowd the night sky are revealed as rare, isolated temporary furnaces separated by years of empty space, burning their finite fuel in a universe that is expanding away from itself at an accelerating rate. But it gets worse, because the room and the planet it sits on, and the star that lights it and the galaxy that contains that star, are not merely temporary in the way that all physical things are temporary, subject to wear and decay and the slow erosion of time. They are temporary in a more absolute sense. They exist within a thermodynamic context that has a direction and a destination, and the direction is toward emptiness, and the destination is a state in which nothing like them can exist. The room will not simply age and crumble. The matter it is made of will, given enough time, dissolve, through proton decay or quantum tunneling or the slow evaporation of whatever black holes eventually form from its remnants, into radiation and the lightest possible particles, dispersing through an ever-expanding void. The room will become part of the universe's background noise, part of the thin, cold, uniform distribution of energy that is the cosmos's final state, and the planet will dissolve, and the star will fade, and the galaxy will darken star by star over trillions of years, until the last red dwarf exhausts its fuel, and the Milky Way, or whatever merged structure it has become by then, is a cold, dark collection of stellar remnants drifting through an expanding universe in which no other galaxy is visible, no other light source exists within the observable horizon, no signal from any other structure can ever arrive. The universe will have separated itself into its final configuration, isolated, thermodynamically exhausted, causally disconnected islands of cold matter, each one proceeding toward its own dissolution in a silence that is not merely the absence of sound, but the absence of any physical process that could produce or transmit or receive any signal of any kind. This is not a scenario that requires any unusual physics. It does not require the big rip or proton decay or any speculative extension of the standard model. It requires only the physics we already know, the second law of thermodynamics, the expansion of space, the finite supply of stellar fuel, the Hawking radiation that will eventually evaporate the black holes. These are not hypotheses. They are the best supported conclusions of modern physics, tested against observation, refined over decades of theoretical and experimental work, and consistent with everything we currently know about the universe. The heat death is not a speculation. It is the expected outcome of the laws of physics as they are currently understood, applied to a universe that began in a low entropy state and has been moving toward equilibrium ever since. There is a version of this story that ends with a kind of philosophical acceptance, with the observation that the universe's thermodynamic fate is so distant and the present moment so vivid and immediate that the appropriate response is to focus on the present, to find meaning in the brief window of cosmic time in which structure and experience and connection are possible. And there is something genuine in this response. The present moment is real. The experience of being alive in a universe that is still young enough and energetic enough to support consciousness is extraordinary. The fact that the universe will eventually reach maximum entropy does not diminish the reality of what is happening now, in this moment, in this room, in this brief and improbable arrangement of matter that is capable of being aware of itself. But the acceptance is also incomplete, because the thermodynamic fate of the universe is not merely a distant future event that can be bracketed off from the present. It is the context in which the present exists. It is the frame within which every moment of experience, every structure, every connection, every event occurs. And the frame matters. The knowledge that the universe is moving toward maximum emptiness, that the structures we inhabit are temporary, that the connections we form are impermanent, that the awareness we possess is a brief and local exception to the universe's overwhelming preference for disorder. This knowledge changes the texture of the present, even if it does not change its content. It changes the way the night sky looks, not the physical appearance, and the stars are still there, the galaxy still faint smudges at the edge of visibility, the Milky Way still arching overhead on a clear dark night. But the meaning of what you are seeing is different when you know what you are seeing. You are not looking at a permanent backdrop. You are looking at a snapshot of a process, a moment in the universe's thermodynamic history, captured in the light that has traveled across years and centuries and millennia to reach your eyes. The stars you see are not the stars as they are now. They are the stars as they were when the light you are receiving left them, years ago, centuries ago, thousands of years ago. The universe you observe is always already the past. The present universe is invisible, hidden behind the light travel time that separates you from everything beyond your immediate neighborhood, and the stars you are looking at are burning. Right now, in the present that you cannot see, they are consuming their fuel, generating their entropy, moving along their thermodynamic trajectories toward the white dwarfs and neutron stars and black holes that will be their eventual remnants. The light you see is the light of processes that are already further along than the light shows. The universe is always ahead of its own image, always further down the road toward emptiness than the light reaching your eyes suggests. This temporal gap between the universe as it is and the universe as it appears is one of the subtler forms of cosmic emptiness, not the emptiness of space between atoms or between stars or between galaxies, but the emptiness of the present moment. The fact that the universe as it actually exists right now is inaccessible to any observer. Every observation is an observation of the past. Every image of a distant galaxy is an image of a galaxy, as it was millions or billions of years ago. The present universe, the universe as it is at this exact moment, across its entire extent, is something no observer can ever see. It exists, but it is permanently hidden behind the finite speed of light and the vast distances that light must cross to carry information from one place to another. The universe is not merely spatially empty, it is temporally opaque. The present is invisible, the past is all we can see, and the past we can see is growing older all the time. The light from the most distant galaxies has been traveling for billions of years, and the galaxies that emitted it may no longer exist in the form they had when the light left them. We are surrounded by ancient light, carrying information about a universe that is already different from the one that produced it. The cosmos we observe is a palimpsest, a layered record of different moments in the universe's history, all arriving at our instruments simultaneously, all appearing to exist in the same present moment, but actually representing a vast range of different pasts. And this leads to something more disturbing, because if the present universe is invisible, if all we can observe is the past, then our understanding of the universe is always incomplete in a fundamental way. We can reconstruct the universe's history from the light that has reached us. We can infer the universe's large-scale structure from the distribution of galaxies we can observe. We can predict the universe's future from the laws of physics and the initial conditions we can measure. But we cannot observe the universe as it is. We can only observe the universe as it was. And the universe as it was is not the universe as it is. And the universe as it is not the universe as it will be. And the universe as it will be is a place where none of the structures we currently observe will exist in their current form. The universe is always already elsewhere, always already further along its thermodynamic trajectory than the light reaching our eyes suggests, always already emptier, colder, more dispersed than the image we receive. The image is beautiful. The image is extraordinary. The image is the product of billions of years of cosmic evolution, of the formation of galaxies and stars and planets and the improbable chemistry of life. But the image is not the reality. The reality is ahead of the image, moving away from it at the speed of light, receding into a future that is darker and emptier and more final than anything the image shows. Go back to the atom one more time. Go back to that cathedral of empty space with its grain of sand nucleus and its electron tracing its probabilistic path through the void. This is where the descent began, with the discovery that the matter you stand on, the matter you are made of, is mostly nothing. That the solidity you feel is a force, not a substance. That the fullness of the world is a perceptual artifact, a useful fiction constructed by a nervous system that was never designed to perceive the true proportions of the reality it inhabits. And now hold that image alongside everything that has been added to it since. The solar system, mostly void with its rare islands of matter separated by distances that light takes minutes and hours to cross. The interstellar medium, nearly perfect vacuum, with its 1 atom per cubic centimeter and its light years of cold silence between the stars. The galaxy, a sparse scattering of isolated nuclear furnaces separated by years of empty space, embedded in a vast halo of invisible dark matter that outweighs the visible stars by a factor of 5 to 10. The cosmic web, dominated by voids hundreds of millions of light years across with thin filaments of matter tracing the boundaries between the empty regions. The expanding universe, driven apart by dark energy, carrying the distant galaxies beyond the cosmic horizon, severing the causal connections between structures, moving toward a future of permanent isolation and thermodynamic exhaustion. Hold all of this simultaneously, not as a sequence of facts, but as a single picture. A picture of the universe as it actually is, at every scale, from the inside of an atom to the edge of the observable cosmos. A universe that is, at nearly every scale, composed primarily of nothing. A universe in which matter is the exception, structure is temporary, and the dominant feature of the cosmos, at every level of organization, from the subatomic to the cosmological, is emptiness. This is the picture that the science produces, not a picture of a universe full of stars and galaxies and the busy complexity of matter organizing itself into ever more elaborate structures, but a picture of a universe in which the stars and galaxies and the complexity of matter are thin, temporary, improbable exceptions to the overwhelming rule of void. A universe in which the matter we can see represents 5% of the total energy content. A universe in which even that 5% is separated by distances so vast that the matter is, for most practical purposes, alone. A universe in which the invisible dark matter and the invisible dark energy, the 95% we cannot directly detect, are shaping and driving the cosmos in ways we are only beginning to understand. And the picture is not finished. The universe is not a static object that can be fully described and set aside. It is a process, a thermodynamic process moving in a direction with a destination. And the direction is toward emptiness, and the destination is a state of maximum entropy in which nothing like the present universe can exist. The picture is not finished because the process is not finished. The expansion continues. The entropy increases. The stars burn their fuel. The gradients are consumed. The structures dissolve. The universe moves moment by moment toward the cold, dark, featureless equilibrium that is its ultimate state. You are inside this process. You are part of it. The atoms in your body were forged in the cores of stars that died before the sun was born. Stellar remnants scattered through the interstellar medium, gathered into the molecular cloud that collapsed to form the solar system, incorporated into the chemistry of the early Earth, cycled through billions of years of geological and biological processes before being assembled into the configuration that is you. You are made of the universe's matter, organized by the universe's processes, powered by the universe's energy gradients, and subject to the universe's thermodynamic laws. You are not separate from the cosmos. You are a local and temporary expression of it, and you are aware of this. This is the thing that does not fit neatly into the thermodynamic picture, not because it contradicts the physics, but because the physics has nothing to say about it. The second law of thermodynamics describes the direction of entropy. It does not describe the experience of being an entropy-generating system that knows it is generating entropy. The equations of general relativity describe the curvature of spacetime. They do not describe the experience of being a conscious observer embedded in curved spacetime, looking outward at the universe and inward at the self simultaneously. The physics is complete, as far as it goes, but it does not go all the way to the experience of being here inside the universe, aware of what the universe is. That awareness is yours. It is happening now, in this moment, in this brief and improbable window of cosmic time. The universe is 13.8 billion years old. The sun has approximately 5 billion years of fuel remaining. The last red dwarf will die in perhaps 10 trillion years. The last black hole will evaporate in perhaps 10 to the power of 100 years. And somewhere in the middle of all of this, somewhere in the thin, bright, temporary window between the formation of the first stars and the death of the last, you are here, aware, looking out at the emptiness, knowing what it is. The room is still around you. The floor is still solid. The morning light is still coming through the window. But the room is different now from what it was at the beginning of this descent. Not physically different. The atoms are in the same positions. The forces are operating in the same ways. The light is falling at the same angle. But the room is now understood differently. It is understood as what it actually is. A temporary arrangement of mostly empty atoms, organized by electromagnetic forces into structures that feel solid but are not, sitting on the surface of a small rocky planet, orbiting an ordinary star in the outer regions of a spiral galaxy that is itself a thin, luminous trace on the surface of a vast, dark matter halo, embedded in a cosmic web of filaments and voids, expanding away from every other structure in the universe at an accelerating rate, moving toward a thermodynamic future in which nothing like this room or this planet or this star or this galaxy will exist. The room is extraordinary, not because it is special. It is not. It is one of an enormous number of similar arrangements of matter on one of an enormous number of similar planets orbiting, one of an enormous number of similar stars in one of an enormous number of similar galaxies. It is not special, but it is here. It exists. It is one of the universe's improbable, temporary, thermodynamically costly exceptions to the rule of emptiness. And inside it right now, there is awareness. There is the experience of being present in a universe that is mostly absent. There is the strange, fragile, improbable fact of consciousness, of a collection of atoms that knows it is a collection of atoms, that can trace the descent from the familiar to the cosmic, that can sit with the full weight of what the universe actually is and not look away. But the awareness is not permanent. Nothing is permanent. The awareness will end, not because the universe will end, but because the physical conditions that support it will eventually cease to be available. The gradients will be consumed. The structures will dissolve. The improbable arrangements of matter that give rise to consciousness will relax toward equilibrium, as all improbable arrangements eventually do. The awareness will become part of the universe's background, part of the thin, cold, uniform distribution of energy that is the cosmos's final state. Not destroyed, not annihilated, simply dispersed, simply returned to the void from which it was briefly, improbably, extraordinarily assembled. And the void will remain, expanding, cold, dark, featureless, patient in the way that only something without consciousness can be patient, not waiting, because waiting implies the experience of time passing, and in a universe at maximum entropy there is no experience of any kind, simply persisting, simply being the final state of a system that began in extraordinary organization and moved, over an incomprehensible duration, toward maximum disorder. The void will not know that it was once full of stars. It will not remember the galaxies, or the planets, or the living things, or the brief, improbable moments of awareness that flickered through the cosmos during the stellar era. It will not mourn the loss of structure. It will not notice the silence. It will simply be what it is, the universe at equilibrium at the end of its thermodynamic story, expanding forever through a darkness that contains nothing capable of observing it. This is the final consequence of the emptiness, not the emptiness of the atom or the solar system or the galaxy or the cosmic void, though all of these are real, and all of them are part of the picture. The final consequence is this: the universe is not a place that is full of things and also contains some emptiness. It is a place that is fundamentally, overwhelmingly, and increasingly empty, in which matter and structure and energy gradients and consciousness are temporary, and local exceptions that will eventually dissolve back into the void from which they emerged. The fullness you feel, the solid floor, the warm light, the dense and present world of ordinary experience, is real. But it is also a brief disturbance, a local fluctuation, a temporary departure from the universe's natural state, which is darkness and cold and silence, and the patient, indifferent expansion of space through which nothing moves and nothing happens, and nothing is aware of anything at all. The descent is complete. You have followed the emptiness from the inside of an atom to the edge of the observable universe, and from the present moment to the thermodynamic end of everything. You have seen the void at every scale. The void inside matter, the void between planets, the void between stars, the void between galaxies, the void of the cosmic web's great empty regions, the void that dark energy is creating by pulling the universe's structures apart, the void that entropy is creating by consuming the gradients that maintain those structures. You have seen the universe as it actually is, rather than as your senses present it. And what you have seen is not a universe full of things. It is a universe full of nothing with rare, temporary, improbable exceptions. The exceptions are real. The stars are real. The galaxies are real. The planets are real. The living things are real. The awareness is real. But they are exceptions. They are the universe's brief, bright, thermodynamically costly departures from its natural state. And the natural state is always there, surrounding them, underlying them, waiting with the patience of something that has no experience of waiting. The vast, cold, dark, expanding emptiness that is the universe's dominant feature, its ultimate destination, and its most honest self-description. You are one of the exceptions. You are here in this room, on this planet, in this galaxy, in this brief window of cosmic time, aware of the emptiness that surrounds you at every scale. The floor beneath you is mostly nothing. The star above you is burning its last reserves of borrowed time. The galaxy around you is drifting through an expanding universe that is carrying everything else beyond the horizon of what can ever be reached. And you know this. You are sitting inside the universe's most improbable exception, consciousness, awareness, the capacity to understand the context in which you exist. And you are looking out at the void that is the universe's most fundamental truth. The void does not look back. It has no eyes. It has no awareness. It is simply there, vast, cold, dark, expanding, patient and permanent in a way that nothing made of matter can ever be. It was there before the first star ignited. It will be there after the last black hole evaporates. It is there now, between every atom of every molecule of every cell of your body, between every planet of every solar system of every galaxy, in the observable universe, beyond the cosmic horizon where the light of distant galaxies has been redshifted into invisibility, in the great empty regions of the cosmic web, where the universe has left almost nothing behind. The void is the universe's natural state. Matter is the disturbance. Structure is the exception. Consciousness is the most improbable exception of all. A brief, local, thermodynamically costly arrangement of matter that is capable of understanding its own improbability, its own temporariness, its own place inside an ocean of emptiness that it can measure and describe but never escape. The morning light is still coming through the window. The room is still here. The world still feels full and present and real. But now you know what that fullness is made of. You know what lies beneath the solid floor and behind the warm light and inside the dense, present, ordinary world of everyday experience. You know that the universe is not full. You know that the matter you stand on is mostly empty space, and the solar system you orbit in is mostly void, and the galaxy you inhabit is mostly darkness, and the universe you are part of is mostly nothing, and the nothing is expanding, and the expansion is accelerating, and the structures that interrupt the nothing are temporary, and the gradients that maintain those structures are finite, and the awareness that is currently contemplating all of this is the most fragile and improbable thing in the observable cosmos. You know all of this, and the room is still here, and the light is still warm, and the world still feels full, and that feeling, that persistent, biologically constructed, evolutionarily ancient feeling of a world dense with presence, is now something different from what it was before. It is not a truth. It is not a lie. It is a gift from a nervous system that was built for survival, not for cosmic comprehension. A gift that allows you to function, to move through the world, to form connections and build structures and maintain the improbable arrangements of matter that constitute a life. A gift that filters out the void so that you can inhabit the exception. But the void is there. It has always been there. It will be there long after the exception has dissolved back into it. The universe does not end with a dramatic final event, not with an explosion, not with a collapse, not with a last great catastrophe that brings everything to a close. It ends, if ending is even the right word, with distance, with separation. With the slow, patient, irreversible process of structures drifting apart, gradients being consumed, matter dissolving, awareness ceasing, and the expanding void growing larger and colder and darker and more complete, until there is nothing left to interrupt it, and nothing left to notice that there is nothing left, and the silence is so absolute and so permanent that the word silence no longer applies, because silence is what you call the absence of sound in a place where sound was once possible, and in the universe's final state nothing was ever possible, and nothing will ever be possible again, and the darkness will simply be what it is, the universe, at rest, at last, forever.